Good morning, everyone. Good day, good evening, depending where you are. Lanssina, Mrs. Eva, can you confirm you are in the room today? I can see your names. If you can open your mics and cameras, that will be also great. Before we start, we will continue admitting participants in the room. And we are having today a very large audience, and we thank the participants, all of you, to stay with us.
Hi, Florencia. Just to confirm, can you hear me?
Yes, we can hear you.
Thank you.
Thank you, Nomagugu. Thank you so much. We can see your video as well.
Okay.
And Lanssina is here. Ezekiel is also here. So let us begin today. We have a program to cover today. So thank you very much. So welcome everyone to Nuclear Pathways 2026, the second edition of Newcomers for Nuclear Global. And it's a great honor to have all of you today. Whether you're joining us from Nairobi, Bogota, Dhaka, Vienna, from Accra, Tokyo, or Riyadh, maybe you can drop on the chat. Where are you joining us? You can introduce yourself to know where are you currently located. And please look around you. I mean, not at the screen, but at the number of today's first session. Over 1,000 participants from 95 countries from every continent on this planet, engineers, scientists, students, researchers, policymakers, advocates, people at the very stage of their journey, united by one thing, a belief that nuclear technology matters and that learning about it shouldn't only be a privilege reserved for a few. So that's why all of you are here. And Newcomers for Nuclear Global was built on a simple conviction that the next generation of nuclear professionals shouldn't have to wait for an opportunity, shouldn't have to pay for access to knowledge, and shouldn't have to navigate this field alone. So this program is free of charge. It always has been since the first edition, not because knowledge is cheap, it's because it's so important to put behind a barrier. What you have access to over the next 2 weeks is the result of months of work by the team that operates across time zones, languages, and continents, and a team that made hundreds of calls, sent emails, and coordinate with institutions from 5 continents, all because we believe in you and this community, in what happens when people like you are given to the access of these materials of the faculty. So I only want to speak a few words about the faculty, that we can truly understand the collaborative, what the program represents. We have assembled a remarkable group of professionals, specialists from the IEA, from the NEA, Nuclear Energy Agency, engineers from operating nuclear power plants in Canada, Egypt, and Chile, scientists from universities in Ghana, the United States, Kenya, and Morocco, policymakers, regulators, legal experts, communication leaders, people who have spent decades at the frontier of this field. So they are here voluntarily, generously, freely, because they believe in what you represent. They are here to give you not just their knowledge, but their experience, their mistakes, their breakthroughs, the things that not a textbook teaches you. So over the next 10 days, you will move through the full breadth of the nuclear world, from the foundations of reactor physics to the politics of non-proliferation, radiation protection, to radioactive waste management, from nuclear safety culture to data analytics and artificial intelligence, from nuclear medicine in Africa to the financial architecture of building a program from the scratch. So you will see the insights of nuclear facilities through virtual tours that most professionals spend entire careers waiting to access. So this is not an narrow curriculum, this is the full map. But I want to be honest with you about something. The lecture matters, the speakers matters, but you are the one who matter more. What makes nuclear pathways different is not the program, it's the community, it is a conversation that happens in the chat when a participant from Bangladesh asks a question that a participant from Bolivia has been thinking about for years. So it is the connection made between an engineer from Nigeria and a researcher from Korea who discover they are working on the same problem from opposite sides in the world. So it's the pure network that you build here in this virtual space that will outlast every slide in every session. You are not observers of this program, you are the most important ingredient. So the nuclear sector stands as at the pivotal moment. The world is looking for clean, reliable, scalable energy. The world is asking harder questions about climate, about security, about equity. And the world needs nuclear professionals who are technically prepared, globally connected, and deeply committed to getting these decisions right. So that is you. That is in this room. 1,000 people from 95 countries or more, 2 weeks, countless possibilities. So we have prepared everything we can for you. The rest is yours to build. So welcome to the Nuclear Pathways, and let us begin. So behind the team, I would like to acknowledge my dear colleagues, Lanssina, the main coordinator of Newcomers for Nuclear Global, who gave us the opportunity to Eva Gyane, my dear colleague from Austria, and is also an important collaborator of Wing Global Groups of Expertise, and myself. So we are deeply honored to be with all of you today. So I'd like to pass the microphone to my dear colleague Lanssina first. If you can give us some welcoming remarks, we really appreciate that. Please, Lanssina, over to you.
Okay, thank you so much, Florencia. Do you hear me very well?
Yes, we can hear you well. Please, you can proceed. Thank you.
My first word is for you and Eva, who's Eva is an amazing team. Nothing is sharp and good made at this time. Thank you so much for your collaboration. Thank you so much for your engagement. I wish you to have a long life, impact your community, your family, your continent, and the world. Thank you so much. For this word, dear participants, speaker, moderators, and partners, a warm and enthusiastic welcome to the second edition of the Newcomer for Nuclear Global Summer School 2026 from August 3 to August 14, 2026. We are embarking on incredible 10-day virtual journey to the future of nuclear science, technology, and policy. We are truly blown away by the scale of the global communities this year. Over more than 1,000 passionate participants joining from more than 95 countries, more than 3 world-class speakers spanning 5 continents, more than 20 expert moderators, guidance or deep dive discussion. Whatever you are a student, a young professional, or emerging voice from a newcomer nuclear nation, this summer school is designed as a collaborative meeting point. Over the next 2 weeks, we will engage with virtual topics ranging from safety culture and reactor technology to non-proliferation project management and strategic issues. Thank you for bringing your curiosity, diverse background, and unique perspective on the table. Let's shape the future of clean energy and nuclear innovation globally. Get ready, stay active, and enjoy the program. Wem'Afrika. Thank you so much.
Thank you so much for those words, Lanssina. Those are very inspiring, and we are here in the second edition with all the entire community. So this is a great milestone. Now I'd like to pass the floor to our dear colleague, Eva Gyane from Austria, who's joining us now from Austin. She's now attending the INMM conference. So please, Mrs. Eva, over to you. Thank you.
Good morning, everyone. I'm so happy to welcome you to this amazing program, to Nuclear Pathways 2026. As has already been said, over the next 2 weeks, you will hear from 30 speakers across 5 continents on so many different subjects, ranging from nuclear energy, safety culture, medicine, risk assessment, non-proliferation, project management, communication, etc., etc. That is really an extraordinary breadth of knowledge to have assembled in one place. Let's just explain to you why we built this program before I hand over back to Florencia. First of all, let's start with the problem we are actually trying to address here. Across many countries in the world, in particular on the African continent, energy scarcity remains one of the defining barriers to development. You have hospitals without reliable power, industries that cannot scale, students studying by candlelight. This is the daily reality of hundreds of millions of people, and it is precisely why the nuclear field and the people who choose it to work in it matter so much right now. Meeting that challenge requires something that cannot be imposed, that is capacity, trained people, engineers, regulators, communicators, project managers, safety specialists, policy experts, a whole generation of professionals who understands this technology well enough to deploy it safely, responsibly, and to the benefit of their own countries. That is the gap that this summer school wants to help to close. This is capacity building in the truest sense, an investment in the people who will shape the nuclear future of their countries over the next decades. This program is completely free of charge. Why? Well, this was our deliberate choice. We do not want your professional development to depend on how much money you or your family have. And talent has no geography. It should have no price tag either. If you are here today, it is because you are curious and committed to register, not because you could afford a fee. And that is exactly how it should be. I want to be direct with you about how to approach the next 10 days. This summer school is not simply a lecture series to sit through passively. Think of it instead as an introduction, a guided tour through many of the different rooms in the house of nuclear science, technology, and policy. There's energy, medicine, safety, non-proliferation, communication, project management. And each one of these is a legitimate career path, and most of you have not yet had the chance to properly explore any of them. So here is my honest advice to you. Participate actively, ask questions, and don't be afraid to ask. And talk to each other across your countries and time zones about what you are hearing. We have created the WhatsApp group, so it's the best means of communication. And you will see how the value of this program will scale directly with how much of yourselves you bring into it. What you hear over the next 2 weeks may genuinely influence your career choices. Someone in one of these sessions may describe a field you have never considered, and it may become the work of your life. That has happened before, so please be open that this may happen again. Before I close, I want to take a moment to properly thank the people who have made this possible, because a program like this does not build itself. First of all, to my dear colleagues, Dr. Florencia Renteria del Toro from Mexico and Mr. Lanssina from Burkina Faso. Thank you. You have worked tirelessly for months to put all this together. And what you have built is genuinely something to be proud of. I would also thank every one of our speakers. They are all accomplished professionals from 5 continents who have made themselves available to you completely free of charge, simply because they believe in sharing their knowledge with the next generation. Thank you. And to our moderators who will guide you through these sessions, keep the conversations flowing, and make your questions get heard. Thank you. And last but not least, to our partners Wem'Afrika and Women in Nuclear Global, whose collaboration and belief in this mission made Nuclear Pathways possible. Thank you for standing behind this program and behind all of you. So, to all our participants, welcome. You are joining a community of emerging nuclear professionals who 10 days from now will know this field and possibly your own future within it a great deal better than you do today. Ask questions, show up, take this seriously, because we have taken you seriously enough to build this for you at no cost with the very best people we could bring to the table. Thank you, and I hope you enjoy Nuclear Pathways 2026.
Thank you so much for those words, Mrs. Eva. Those were very impactful to the community, and it's a great pleasure to work together with you and Lanssina and the rest of our partners and colleagues from the community. So, as you said, this initiative cannot be powered alone. So this year, we are also continue joining with Wing Global and Wem'Afrika as partners and allies in this process. So now I'd like to invite my colleague Ezekiel Ashai. He's the unit lead for the Security Department of Wem'Afrika in Ghana, that he can give us some remarks about today's event. So please, Ezekiel, over to you. The floor is yours. Thank you.
Thank you so much. Thank you so much. I'd like to
Ezekiel, we cannot hear you well. Probably, can you increase the volume? Thank you so much. Sorry for interrupting you.
Is it okay now?
Yes, now it's better. Please, over to you. Continue.
Thank you very much. Greetings to our distinguished guest speakers, partners, and then everyone who has joined us today. My name is Ezekiel, and I'm speaking from Accra, Ghana. On behalf of Wem'Afrika, I would like to warmly welcome each and every one of you. We are truly honored and grateful for the opportunity to partner on this important project. Your presence today demonstrates your commitment to learning, collaboration, and advancing nuclear education. I also bring you warm greetings from our founder, Pauline, who extends her appreciation for our partners, facilitators, and participants. We wishes you a productive and inspiring training and encourages you to take full advantage of this opportunity. We are all aware that the challenges facing our world, whether related to peace, security, climate change, public health, or energy, cannot be solved by one individual or one organization alone. They require collaboration, partnership, and a shared commitment to building a safer and more sustainable future. So for those who are hearing about Wem'Afrika for the first time, we are a non-profit organization founded in Cameroon with a vision of empowering communities across Africa through research, training, policy engagement, and community development. We believe that sustainable development begins with knowledge and that every individual has the potential to become a catalyst for positive change. Our work is carried out through 7 key departments. We have the gender, human rights, humanitarian, conflict management, capacity building, environment, and security. Today, I have the privilege of representing the security department, where we focus on promoting awareness, education, and professional development in areas such as nuclear security, global security, nuclear protection, and food security. Over the years, Wem'Afrika has remained committed to creating learning opportunities for young professionals and students across Africa. Through our webinars, workshops, policy discussions, research initiatives, and community engagement activities, we have reached hundreds of participants from different countries. Our security department alone has organized more than 7 international webinars, bringing together over 10 experts from academia, government, and international organizations to discuss emerging issues in nuclear safety and peaceful nuclear applications. Today's training represents another important milestone in that journey. This training is not simply about gaining a certificate, it is about becoming part of a growing community of professionals committed to strengthening peace, security, and sustainable development through education and responsible leadership. Once again, I would like to thank our partners, facilitators, speakers, and every participant for making this initiative possible. Your commitment to learning today is an investment in Africa's future and in a safer world for all. I wish you a successful, engaging, and impactful learning. Thank you and welcome once again. Thanks very much.
Thank you very much, Ezekiel, for that inspiring message. And before we continue with the program, we want to thank Wem'Afrika, always standing next to us, as well as being global, the community. We are a family together, and we really thank you deeply for this great support that you have been giving us through we started this collaboration. So now we would like to share briefly the program that you have received via email. Today we will have we are concluding with the opening remarks, and we will have follow-up the nuclear engineering landscape lecture given by Dr. Jeremy Whitlock from Canada, and who's also attending to the INMM conference in Austin, Texas. We'll follow up with a lecture from Dr. Patrick Carter-Cortez, Applied Nuclear Physics, and we will conclude the day with the participation of Nuclear Energy Agency colleagues, Mrs. Beatriz Hernandez and Christophe Tocco. They will talk about the role of nuclear energy in the international frameworks and the future of nuclear, specifically how the Nuclear Energy Agency is complying this role globally. So just a brief note before we continue. Part of the school requirements are to attend 80% of the sessions. We understand most of you are joining in your working hours. So if there is any problem that you encounter or any specific case that you are not able to attend, please just email us privately or in the chat also as well. You have the WhatsApp group community. So please just let us know that we know that you're having some challenges to overcome. The recordings will be available after each day when we're finalizing the lectures, that you can revisit the materials in case that some of the sessions were not fully covered, probably if you're experiencing some network issues, internet connection, etc. So please just feel free to drop a message to us. At the end of the 2 weeks competition, we will have a small test based on the lecture contents. That'll be very generic. We will give you all the details, and you will have enough time to complete the test. So don't worry about it. The test will be conducted online, of course, and submitting the summer school survey of satisfaction to receive your certificate of completion of the program. So please just keep this in mind. We will also share these details through email, but we wanted to let you know that we want to make this a space in a flexible way, that your learning process cannot stop. So we want you to continue growing and learn most out of the best of this program for today. So now I would like to give the floor to my dear colleague Lanssina, that will be introducing today our moderator, Mrs. Nomagugu, and Nomagugu will be introducing Dr. Jeremy Whitlock. Please, Lanssina, over to you. Thank you.
Okay, thank you so much, Florencia. I hope you hear me very well. I'm going to presenting our first moderator, a strong woman from Zimbabwe. She's a control and system engineer from Zimbabwe, committed to making science and engineering meaningful in people's life. Alongside her work in STEM education and his interest in nuclear energy and security, and focus in sharing practical valuable knowledge. Ndlovu holds a bachelor's and honor degree in electronic engineering from the National University of Science and Technology in Zimbabwe, and a Master of Science in Advanced Control and System Engineering from the University of Manchester in the UK. She aims to use her skills to solve a real-world problem and help oversee the possibility with science and technology. Thank you so much, Nongo, to join us. You are very, very strong, and we hope you are going to contribute. You are going to contribute to shape the future of nuclear science and nuclear energy in Africa. Thank you so much. The floor is yours.
Thank you so much, Lanssina, for the kind welcome and warm remarks. Good morning, good afternoon, and good evening, wherever you're joining us from. Welcome to the Newcomers for Nuclear Global Virtual Summer School 2026. My name is Nomagugu Ndlovu, and I'll be your moderator for today's session. So today's lecture is titled the nuclear energy landscape. And our speaker will be Dr. Jeremy Whitlock. Please keep your microphones muted during the lecture, and you may submit your questions in the chat at any time, and they'll be addressed during the Q&A after the presentation. A little bit about our speaker, Dr. Jeremy Whitlock. He is a private consultant and adjunct professor at McMaster University, who recently returned from 8 years at the IAEA as a senior technical advisor and section head in the Department of Safeguards. His responsibilities included preparations for safeguarding advanced reactor and fuel cycle technologies. Prior to this, Dr. Whitlock spent 22 years at Chalk River Laboratories in Canada as a manager of non-proliferation and safeguard program, and as a reactor physicist in CANDU and research reactor design. Dr. Whitlock received a Bachelor of Science in Physics from the University of Waterloo in 1988, and a Master of Engineering and PhD in Reactor Physics from McMaster University in 1995. Please join me in welcoming Dr. Jeremy Whitlock. Doctor, the floor is yours.
Thank you so much for that introduction, and good morning, everybody. And thank you for inviting me and thank you for allowing me to speak to you today on this important topic and to help kick off this important school. Now, let me share my screen here for my slides. Go and this and there. So hopefully you can see that, and hopefully you can all hear me. So today I'm going to be talking to you about nuclear energy, the landscape, where we are, and where we are going. So it's to sort of set the foundation. I have been in this industry for a long time, for over 30 years. I grew up in the industry. My father worked in the nuclear industry, so I have been a nuclear person my entire life, and I have watched it evolve from the mid-1970s until today, and it's been a very exciting journey, and I want to share some of that with you today, to let you know where we came from, also, because that's also as important as where we are, and also then where we are going. So there we go. I wanted to start off by, I don't know if you can see, I'm getting these lobby notices as well on the screen. I wanted to start off by noting that as important as nuclear is, and as much as we love it, and as much as it contributes to social health and prosperity, and also the social consciousness, and as prevalent as the nuclear topic is in the social zeitgeist, in the minds of people, whether it's negative or positive, everybody knows this topic, and everybody has an opinion on it. It really has a huge social impact, but its global energy contribution is still rather small. We are still a fossil-driven world, very much so. And nuclear only contributes 4% of the primary energy. So this is not electricity, but the primary energy itself. Electricity is something around 10% globally. So 4% of the primary energy out there. So it's a little bit more than solar. It's around the same as each of the renewables, but it pales in comparison to the fossil. So that's kind of interesting that it has this massive global impact, in technically as well as socially, and yet it's a small contribution in terms of a small contribution to the energy supply. There we go. So what is the social impact? So it's not just electricity supply, of course. It's enabling a safer world for everybody. So it contributes to health and nutrition, food and agriculture, and this is mainly due to radioisotope production, monitoring and bettering of water supply, and improving of the environment, all of the industrial applications. And then we get into the nuclear safety and security that people are probably more apt to bring up first when you ask them about what their concerns are about nuclear. Then there's the nuclear power and the fuel cycle, which provides about 9 or 10% of the electricity. of the world, and then nuclear non-proliferation is the enabling structure, the infrastructure that allows all of the above to be shared amongst the nations to enable better health and nutrition and to provide electricity. So this is the huge social impact that it does have. I want to go back because to go forward, we have to acknowledge where we came from. Everything changed with nuclear fission's discovery in the middle of the last century. So I can't believe that we are actually now coming up to the 100th anniversary of the discovery of nuclear fission, which was in 1938, at the end of 1938, when fission was discovered in Germany. And Lisa Meitner and Otto Frisch came up with the explanation for nuclear fission and the definition, and it immediately revolutionized science and technology. Can everybody just please mute their microphone? Thank you. It immediately revolutionized science. It was the culmination of nuclear science over the first half of the last century. I'm not just saying this because I love the technology, but it really did bring together all of the golden era of nuclear science that was growing from the turn of the last century of the 20th century until that time. All these theories were being developed and the structure of the atom, but they didn't quite know everything until it all came together in the 1930s, when so many Nobel Prizes were earned. And fission itself brought together all of these theories with experiment, and immediately created, and everybody knew this, a cheaper and essentially unlimited source of radioisotopes. And radioisotopes had been around for decades, just extracting them from uranium ore, for example. And even nuclear medicine had started by that point, but this was an unlimited source of easily accessed radioisotopes. It was a powerful neutron source for material science and applications. And also they knew it was going to be a concentrated source of energy, both heat and electricity. And of course, the first time it was used in this way was in military applications, but a potentially vast fuel supply and no combustion products. So all of these fantastic things happened with the discovery of fission. And then, as I mentioned, radioisotopes are an important social impact. This was, in fact, the first peaceful application of nuclear and energy. So the first application was military. At the end of World War II, the first peaceful application, even as the war was coming to an end and the first reactors were operating, the first research reactors, test reactors, but immediately afterwards, as soon as the larger test reactors were created, you had radioisotopes. Because of course they knew what radioisotopes were, they just now had a way to make them in large enough supply that you could ship them around the world and you can design technologies to use them. So one of the first ways they did this was with cobalt-60 to fight cancer. So now we do this also with gamma rays. We also use radiation created from particles that are accelerated in accelerators. So both of these technologies are used. Gamma radiation is still used around the world. This gamma knife in the picture here is a new version of this technology. And the first time that this was done was in 1951. So only 6 years after the end of World War II, and this was in Canada. It was the first time that cobalt-60 was used to fight cancer. You can use all sorts of radiation, beta radiation as well, for localized brachytherapy, which is putting the isotope right next to the cancer cell, and you can fight cancer, prostate cancer with this. And so an example is lutetium-177, or using gamma from iodine-125, and there's a host of radioisotopes, and this is a very exciting area of nuclear today still. Positron emission tomography, or PET scanners, use short-life radiation emitted from isotopes, mainly fluorine-18 mixed with other molecules. These are made in cyclotrons in hospitals. And then you have longer half-life parents being shipped, whose daughter products are used. And the classic example of this is Moly-99, which is made in research reactors. And this was the one that was made in sort of the 1960s and the 1970s, and today is the workhorse radioisotope in nuclear medicine, or rather its daughter product, technetium-99m, with its 6-hour half-life, is the actual injected isotope used in cameras like SPECT cameras, single positron emission cameras. So globally, 36 million diagnostic procedures per year and 4 million therapeutic, actually fighting disease. And so it's a massive social impact. I also want to talk about research reactors because these were the first reactors built. Hundreds of them have been built around the world. They are an integral part of healthy nuclear science and technology programs. They also are an integral part of healthy people, because this is where we get a lot of our nuclear medicine from. They support research, they support education, they in a huge way support the industry itself, and they support public awareness. Since 1942, since the middle of World War II, you have 849 research reactors have been built in 72 countries, and today 228 research reactors are in operation in 54 countries, and there are 23 research reactors planned for construction in 18 countries. So this is still very much the foundation of the nuclear program. We often just think and talk about the electricity producing reactors and the new designs. So I wanted to start off by talking, this is why I want to talk about where we came from and the fact that it was nuclear medicine and nuclear research reactors that really underpin this other application of nuclear, which affects us in terms of the power production that keeps the lights on and keeps our hospitals running. So research reactors today, because of their convenient location, because they're not on nuclear power generating station sites, especially when they're in a university, as these pictures show on the right-hand side, which is McMaster University, where I am a professor. This is near Toronto, Canada. Because of their easier security access, because of their lower operational constraints, and because of so you can bring people in easily to see. Often you can actually see the actual reactor running, which you can't with the power reactor. And because of their educational mandate, the research reactors are often the public's closest interaction with nuclear science and technology. They always have been, and they remain so today. Okay, now we have the power reactors that the public will automatically think about when you ask them, what does nuclear do? So these are electricity producing reactors, and there are hundreds of them today. Starting in the 1950s, they started to produce electricity. As I mentioned, about 9%. So remember, 4% roughly of the primary energy supply in the world. So, but if you narrow that down to electricity, it's about 9%. So still a relatively small fraction, supplied from about 440 power reactors over a little more than 30 countries. However, it is the second largest source of low carbon power. So it roughly, nuclear will roughly or be slightly less than the renewables. But if you talk about each renewable of their own, solar, wind, geothermal, etc., nuclear is actually the second largest low carbon clean source of electricity today. And you can see today the big users in the bottom right, the USA, China, France, and Russia. So 4 of the P5 or 4 of the nuclear weapon states. The other of those is the UK, which is down there, about a third of the way down the chart. So Atoms for Peace is the way that all of this got started in the 1950s, and those social impacts that I listed before, these are them, starting with health and nutrition, food and agriculture, and nuclear non-proliferation at the end. And those are very specifically worded categories that I used, because these are the categories that the International Atomic Energy Agency focuses on. And so they do have their nuclear power support programs, but also they support the production and sharing of radioisotopes for all of the categories above that in the list. And of course, I've highlighted nuclear non-proliferation at the bottom of the list, because that is the purview of the IAEA. They enable the above access to nuclear, and they do that by providing strong nuclear non-proliferation oversight. Okay, so one way to picture that is this, that you have the non-proliferation treaty, and all of those things that the non-proliferation treaty enables through the work, the facilitation and oversight of the IAEA, you don't want to have nuclear weapons being spread, because nuclear will always have this yin and yang with nuclear weapons, which is how it was created in World War II, and it still has that connection today. So at the IAEA, you have many departments, about over 2,000 staff that are dealing with the aspects of nuclear that it has to offer society, and you don't want to have countries that don't already have nuclear weapons to be developing nuclear weapons, because you can divert nuclear material to a covert nuclear weapons program. So for that, you need, I'm having trouble with these windows popping up about people coming in the lobby all the time. So excuse me for that, because it's stopping me from advancing my slide. There we go. So we have the Department of Safeguards at the IAEA, which is where I worked for 8 years, and there's almost 900 staff that are involved in that on a daily basis. Okay, so we also must acknowledge that everything hasn't been rosy for the last 80 years of nuclear. We've had some major accidents, and this is also a major social impact, and it has led to an attrition of public trust over the years. So these major accidents are 3 Mile Island and Fukushima and Chernobyl, of course. The problem with these accidents, all industries have accidents. In nuclear, it's pretty unique in that any accident, regardless of the health risks, regardless of if people were actually harmed, they tend to be high-profile, globally traumatic events. They get discussed about their impact by everybody on the planet, and each of these accidents has the potential to destroy public trust, and this has been seen. I wish I could turn off these little things popping up. Okay. So in general, public support has dropped after each major accident, but it's generally rebounded, and we are thankfully in a period now where it's been a decade and a half since the last one in Fukushima. So you actually have a generation now that has grown up and are going to university who have not witnessed a major nuclear accident in their conscious lifetime. So students that I talk to now at university in my undergraduate class, they were alive when Fukushima happened, but and this maybe includes many people that are on this call today. But it's not part of their conscious life. They don't remember it happening, and it doesn't affect their opinion of nuclear. So this is where the public is today as well, not just people who are involved in nuclear. However, technically, lessons learned from these accidents have led to improvements in technology, as accidents and industry often do, and improvements in safety, but also in communication, because what leads to negative repercussions is typically not the accident itself, not the lessons learned. For example, Chernobyl had some lessons to be taught technically, but mostly it was about one of the big lessons is the types of reactors we should not be building. But safety lessons. But then most of the world did not have those reactors anyway and had already learned those safety lessons. But the fact is that people associate any reactor with any reactor design that they see. They don't separate the technical aspects of it. So the communicating of this was very important. Fukushima was a classic example of this as well, where the radiation released from the site was not enough to cause damage in the public, health impacts, but the major health impacts were from people being afraid of radiation, being afraid of what was happening at Fukushima, and not believing the authorities, and not understanding what the authorities were trying to tell them, and then evacuating and having accidents, and thousands in fact died, but it was from the response to the fear of the radiation and not from the radiation itself. So we've learned quite a bit about not just the technical aspects of nuclear, but also the importance of communication. So speaking of which, public opinion has gradually been growing as time goes on, and especially lately. Here we go. So gradually growing as people recognize that the benefits outweigh these risks, which is also what the public how the public perceives other technologies. They have risks, they have benefits, and generally the public is accepting of technologies where the benefits outweigh the risks. And you can see here on the right, the public opinion is tracked from the mid-1980s until today, and you can see it's always sort of positive. These are different countries that are shown here, always positive, going up and down. It takes a dip when Chernobyl happened in 1986. You can see them taking a dip. This is the net support, so it's the positive minus the negative, and you can see it taking in the US, taking a large dip and going negative after Fukushima, and in all countries taking a dip, but generally rising again. And so we see today, and over time, it's always been gradually increasing as the public over a very long time coming to terms with nuclear. Part of the reason for this is that there have been very few accidents. So with the aircraft industry, for example, there is an accident every year, and accidents, in fact, in the aircraft industry are a major part of the public's perception of air travel. It does not affect the public's willingness to fly on airplanes. With nuclear, you don't hear anything for, in this case, it's been 15, 16 years since the last one. And then all of a sudden there may be an accident and it becomes this huge event, and there is a reaction. So slowly though, it's been increasing. Nuclear is especially sensitive to public opinion because it needs public support for funding. Even with all of the private companies today that are out there, there's still strong government support is needed, whether it's for granting approvals to build or just funding. And political support depends on public support. Public support also directly is involved in the environmental assessment process. So the years of developing a nuclear technology involve public input. And there are cultural perceptions around radiation waste and safety risks as well, that as I've talked about. So there's not widespread understanding, but there's widespread perceptions about these. And so these directly tie into the level of public support. If you can see on the bottom right, there's it shows the sort of polling, at least in recent years, from different countries. You have the blue, which is the positive, and the gray, which is the negative. And of course, as reflected in the chart just above, you can see the blue slightly outweighs the gray. You have this, what I call a soft middle. Strongly supportive on the dark blue, the strongly supporting public, and then you have the dark gray on the left, which is strongly not liking nuclear. And in the middle is this soft middle. And that's often perceived as, the light blue is often perceived as support. Well, they do support when this question was asked of them. But if there were to be an accident, this is the group that they're kind of on the fence. It sounds good to them when things are rosy, but if there's something negative happening in the world of nuclear, then they will use their sense that, well, I don't understand it, and I think we should maybe not build anymore until we better understand it. So this group will turn on a dime, and this is why the public perception globally responds after an accident so sensitively. So it shouldn't be taken as support. It should be taken as a encouragement for better communication, because this is the group that not the group that's the far right, the dark blue. You need this light blue group and some of that light gray group to be better informed about the impact of nuclear and the impact of the safety of nuclear. And you don't want to be, for example, explaining what radiation means and the safety of radiation when there's an accident, which is what was happening after Fukushima. So global trends tend to increase support today. We're in a period now where there is large public support. I think if there was an accident today, this support would not disappear. There would be a slowing down of the industry, but we would still proceed on. And these global trends today is the longstanding concerns about climate change, which are increasingly concerning the public. Combine that with the digital economy and the electricity needs and the security, more lately, the security of fuel supply on the planet. Where are we going to get our enriched uranium from, for example, but also where are we going to get our natural gas from? And so people in Europe are turning to nuclear in countries that were basically abandoning nuclear only recently. So that's happening now. Public support is in a good place, but I say that tentatively and with warning, because it can change at any moment. And that's unfortunately the world of nuclear. we do need to communicate better. We need to engage stakeholders. Public is a huge stakeholder, but also government and non-government organizations. Major projects, especially nuclear, increasingly today are seeking stakeholder engagement. This has grown, which is good, and also seek not just engaging and communicating, but partnership. You have host communities, indigenous communities in countries like Canada, but around the world, indigenous communities that are being increasingly recognized as the stewards of the land upon which we are building these nuclear plants. And these are the groups that we are making increasingly partners in these projects. Non-government organizations or NGOs, and the general public, demographic subgroups. The evolution of stakeholder engagement has been that in the past we would cite a project and then build a project and then engage the public, which is typically how industrial development has taken place in the past. Now today, increasingly, you engage the public first, and this informs the citing of a project, and then you build. And so I know this is true in Canada today. In that central picture there, you see there's a ceremony with Indigenous people sitting in a circle, and there's a fire in the middle. And these are the Indigenous people of Canada, and you're meeting with them. You're explaining what the technology is. You're bringing them into the tent to talk about how they can take part in the construction of the technology, and then only when you have their support do you build. And if you don't do it that way, the project will take much longer to build and may not get built eventually anyway. So lessons learned for newcomer engagement, whether it's a demographic group or whether it's an entire nation that's a newcomer nation, is start early with the stakeholder engagement. Stay consistent with your message, tailor your strategies to whatever the local context is of the group. Build communication capacity, include communication as an important part of your technology. It is tied to safety as well, because people will get hurt if they don't understand the technology, and they will make decisions if there's an accident, for example. That's when people get hurt, as I mentioned with Fukushima. Innovate in your methods of communicating, empower the communities themselves to understand and to be ambassadors of the technology, and ensure that the messages are aligned between the political groups, the institutional groups, and your stakeholder engagement. So there has to be consistency in the message. So the safety and sense of safety is something that I wanted to make a distinction on. On the left, you have an example of defense in depth, and that's technical safety. That's on the left is how an engineer explains that the radiation will not escape from the fuel of a reactor. On the right, you have the public-facing picture of safety. So this is post-Fukushima, a young child with his arms up being held up by a Geiger counter. And the person with the Geiger counter is wearing protective clothing. And why are they wearing protective clothing? The radiation must be really dangerous, and yet the government is telling us that it's okay. Why are they measuring us? And this is how the public saw the interaction with themselves as the major stakeholder group post Fukushima. You are not safe until you feel safe, and it's very important for nuclear engineers to understand the difference between technical safety and sense of safety. So it doesn't matter how much I tell my wife that I know that I'm aware of when I'm driving the car on the freeway, for example. She's sitting in the passenger seat and she's very afraid and she has anxiety and she's not often having a very enjoyable time. And this affects your blood flow, pressure, and your heart rate, and how you feel about the trip. And so you are not actually safe unless you feel safe. Okay, the look ahead. So over 30 countries have signed the declaration of tripling nuclear energy capacity by 2050 for the reasons that we have discussed, the concerns about climate change, the increase of electricity demand. And it's not just, I mentioned on the previous slide, the digital economy, but it's also countries that don't have electricity now in enough supply that everybody has access to it, becoming countries that have enough electricity supply. And so that's why on the right, I show two charts. The top chart is with some uncertainty in the chart. You have the increase in electricity projected around the world. And below that, I've chosen to show the continent of Africa itself. And you can see that the range goes from 5 times by 2050. So not just tripling, but 5 times at the minimum and 12 times. And this is because you have countries that are living today in energy poverty, wanting to get out of energy poverty and needing electricity supply. As I mentioned, the key drivers of nuclear expansion today are these ones that we talked about. Sustainable development is extremely important in that list as well, especially important to newcomer countries. It's important everywhere, but the countries that want to get out of energy poverty can do it with a variety of technologies, and you want those technologies to be as clean as possible. Expansion of nuclear in the future will include much more diversity of technology, not just two main reactor types, heavy water and light water, and all of the subclasses of those reactors that are out there, especially the light water reactors, but many more types of reactors. Much more distributed deployment, so smaller reactors distributed more remotely, for example, and more private development. But as I mentioned before, this private development still needs government backing, so that's still essential. And increasingly waste management, including what you do when the reactor is finished, the decommissioning, the long-term fuel disposal, the remediation of legacy issues. If you're a country that's been in nuclear for a long time, those are increasingly important as well. Please mute your microphone. Thank you. Thank you. There are new paths ahead in these technologies, which will be discussed in this course, but I wanted to just touch on them at a high level here. You have the pebble bed, graphite high temperature reactors. An example are the pebble bed reactors on the top right, and you can see the picture of the fuel in China for their reactor. Molten salt reactors, integral PWRs, so integral versions of power pressurized water reactors, where the steam extraction is done in the same containment, same vessel as the reactor itself. All of these are now in the mix today. They are technologies, many of them that have been around for quite a while. But what's happening today is because of the receptive environment, you're seeing these being developed. New technologies, but also deployment models. So small modular reactors being taken to remote areas. In the center, you have remote deployment. That's a picture of the north of Canada. Processes involved with waste management in the upper right, transportable reactors and maritime propulsion. We'll talk a little bit about that shortly. In the bottom left, a picture here is the Russian transportable floating nuclear reactor. Fusion is coming along now. Fusion has been around longer than fission, but commercial fusion is taking a long time to be developed. We are seeing today that it is going to be developed by many countries. And a lot of private investment in that. And there are advanced tools and processes as well. So not just in computing, but here we have a picture of a drone in the bottom right. So all of the modern technology and AI being applied to the nuclear world as well. So I touched on this, and let's look a little bit further at it. 80% of the world population lives in a developing country. So that is very, very important to keep in mind. 700 million people lack access to electricity. 2 billion people lack access to clean cooking fuels. Over 800 million people go to bed hungry every night. And this contributes to social challenges and safety. More than 3 million premature deaths per year. So that is energy poverty. And this is very important to me. I wanted to mention it today as well, because it's very important to keep in mind that it's not just the developing countries developing more. It's countries that are already developed. It's countries that are developing and needing to do this, as I mentioned in my previous slide, much more than the developed world. And so you're going to have lots of different types of technologies, and a lot of them are not very clean. So the energy requirements, they need reliable electricity, often small because you have small and fragmented grids, often with weak transmission infrastructure, often distributed in remote areas, rural and remote areas. So today's reactors will not apply. It's got to be reactors that look kind of like these diesel generators you see in Nigeria and on the right. They have to have low land use, especially in densely populated areas. They must be environmentally sustainable. They must have high capacity factor, and it's also heat and electricity because it's for industrialization. So steel production, cement production, fertilizer production, desalination of seawater, and hydrogen production. As important as electricity, it must be done at a reasonable construction cost and a low construction risk as well. And this can complement renewables, but when you build renewable, because these countries also have access to solar power and wind power, but when you have those, you also need to have backup power, and they don't have that. So that needs to be something else, even if you're building a renewable fleet. And so that something else is going to be diesel generators. It's going to be fossil fuel if it's not going to be nuclear. A case study is Namibia. I'm just going to quickly put this up here. It's one of the world's highest income disparity countries. 40% of the country lives in energy poverty. They have sanitation issues, clean water supply issues. At the same time, they are the fourth largest supplier of uranium. They just don't use it. They export it, and you have this disparity between the urban and the rural, energy and no energy. And so electricity is largely imported, most of that from South Africa. They do have a nuclear power program. They have the potential. They have the uranium, and they can even make their own fuel. And you can build up their industrial infrastructure this way, but instead of just exporting the raw material. So they are taking part in the IEA's milestones approach. But it faces a conundrum, because when you look at the country, it's 600 megawatts. 600 megawatts, which is the amount of an SMR being produced. That is their entire national supply. And people often look at that number and say, well, how can 600 megawatts be supplied? You talk to the Namibians and they say, we don't want 600 megawatts. We want thousands and thousands. We want gigawatts. We want gigawatts because we don't want to be continuing to live in energy poverty. We want to expand our use of electricity, and we want to even be able to sell electricity. Namibia should be selling electricity to South Africa, not the other way around, because they are the fourth largest supplier of uranium. And so they are on a long program to get there, working with the IAEA. And I wanted to mention that country specifically at this point. New First World Frontiers. I can't see the title because of these windows that are popping up, but merchant shipping. So you have today large fraction of the greenhouse gases being produced by the cargo ships, the thousands of cargo ships that are on the oceans, moving 10 to 12 billion tons of cargo per year. And this fleet of heavy oil, fuel oil burning or diesel burning ships produces about 3% of the global greenhouse gas emissions. So it's equivalent to a country, these ships that are out there. And there's no reason technically that these large ships can't have a nuclear reactor powering them. And in fact, nuclear reactors have been powering ships for decades, and this is a perfect application because they are at sea for a long time, and nuclear reactors don't need refueling for a long time, but also doing that and also being clean. So the International Maritime Organization has committed to reducing these greenhouse emissions by 20 to 30% by 2030 and net zero by 2050, which kind of ties in with the other net zero ideas around the world. And it's an agency, the IMO is an agency of the UN, so they're committed to the 17 Sustainable Development Goals. They have various non-nuclear approaches, but to achieving this, including wind assist, using the wind for some of the larger ships. But one of these is they're looking at now at nuclear propulsion. The challenges to having nuclear propulsion for cargo ships, for non-military vessels on the oceans is obviously the safety and security and the safeguards. There's the governments and the policies for shipping. They're not built around nuclear at all, and maritime law has to be looked at and integrated. And there's the dependence upon port infrastructure as well. And so this is being looked at today. That's a new frontier. Another one are the digital economy. You can see the growth of electricity there on the right. Behind the meter nuclear, that's having your own dedicated nuclear reactor, providing 24/7 reliable, clean electricity, co-located near the data facility. That's a big demand. 1 to 5 gigawatts per facility. So these are, you can think of 1 gig, that being 1 to 5 nuclear plants. It's just amazing. It's astounding how much electricity this is needed. When you have your own nuclear reactor, you have a reliable supply, you control your own supply, the prices are more stable, reduced transmission needs. And the projections today by 2035, and increasing to 1,300 terawatt hours per year, or for AI alone, that's over 100 gigawatts of continuous power, which is effectively over 100 reactors. So that's what this last bullet here says. New nuclear is roughly 90 gigawatts in this range. And so that's another area where nuclear is being looked at. And this says new first world frontiers, Canada's north. I'm looking at the north of the globe here. And Canada has taken note of the fact that it needs to have more sovereignty in its north around the North Pole. It shares the top of the world with other countries, notably Russia, and Canada is unable to patrol a lot of its waters because it doesn't have nuclear icebreakers and doesn't have nuclear submarines. It needs to get those, but also needs to have small reactors in the north. In the bottom right picture, you see this small community in the north of Canada. So Canada has planned to invest billions of dollars, Canadian dollars, in the north and expanding the energy supply up there. And it's looking at dual-use military civilian infrastructure in nuclear. So nuclear reactors that are possibly on a new military base, supplying electricity to and heat perhaps to a civilian community nearby. This will open up raw resource potential. There's lots of mining that's possible in the north of Canada that you can't get to today. It's a very remote part of the planet, and energy is the key to getting there. Military bases, opening up a new port in the north, and this would be nuclear powered, and also providing nuclear electricity and heat to communities, which today all mostly use diesel generators, believe it or not. So microreactors are being looked at by Canada, and this is a huge niche area for nuclear. And this is regardless of what's being produced for electricity production in the rest of the world. These need to be microreactors that can survive in very unique conditions remotely. And in the remoteness of it, it kind of shares some of the needs for the remote communities in Africa. Just much different climate, but also remote, and needs the safety and the security associated with that. So there's a big role to be played there. Wanted to quickly mention deep geologic repositories. So looking at what happens to the fuel over hundreds of thousands of years. You can't have it in surface facilities that are very safe, but they will not survive a glacier coming when the next glaciation happens. And so Canada, like other countries, is building a deep geologic repository. Finland has one today and is about to start moving fuel into that facility. You need it to be immune to anything happening on the surface for 1 million years. That's a big ask, a big requirement. You take advantage of natural and engineered barriers, and you are able to survive multiple glaciations. And this is the only industrial waste that will survive multiple glaciations. So people are worried about nuclear waste. Ironically, it's the only waste that when we put them in these deep geologic repositories, it would be the only waste that is actually, you know where it is after the next glaciation happens. I wanted to quickly note the value of nuclear organizations, including new newcomers for nuclear. I've got the Canadian Nuclear Society on here on the right as well, but there are that's just an example of the many nuclear societies that are in countries around the world. NAY, Gyane, IYNC, and WIN. These groups, these organizations allow the nuclear industry to pool its resources. These groups do amazing work communicating with the public and addressing the education, as this course is doing today, for the nuclear community, and the industry can donate to that, donate resources, and it's a pooling of resources reaching a lot of people than what one company can do by itself. It creates national and international networks for mentoring, career development, sharing of best practices. It fosters enthusiasm and energy outside of the requirements of work and school. It generates it's a vehicle for generating a communication. It's a medium for communication with the general public and advocacy. It's not linked to any one company. Then it doesn't have the tie to a certain part of the industry. It provides a mechanism for highlighting and addressing needs.
Speaking of big feet,
Please turn your microphone off.
Some of which are not totally unattractive. That reminds me,
Please turn your microphone
gifts
off.
for the kids.
Hello. Thank you. It highlights the needs of a certain demographic. For example, for women and any YGN or YGN networks for young people. And it gives early leadership opportunities as well, which is fantastic. And we are closing the gender gap. I'm almost at the end of my presentation now, but I wanted to talk about the gender gap. On the right, you have the first design team for the first CANDO in Canada in the 1950s. It's a small group, but also it's an all-male group, all wearing suits, no computer in sight. But on the bottom, you have an example of what it looks like today in Canada. That's the first all-female operations crew at the Pickering nuclear plant, one of the largest nuclear plants in the world near Toronto. And they didn't plan this. They just happened to have enough women working in the industry that one night in 2022, they realized that all the women, all the crew in the control room that night were women. So they took this picture, and you can see they're wearing their COVID masks as well. So I know I'm running out of time, so I'll just quickly put these points up here. Women in nuclear and OECD have looked at what you need to do to not only attract more women and recruit them, but to retain them in the industry. So you need to address unique needs of women and how they interact with the men and that kind of thing, and also advancement of women through their careers. So all these things are important. It's not just hiring more women; it's keeping them in the industry and giving them opportunities to advance through the industry, including things like having time to have children and come back into the industry and pick up where you left off and not have disadvantages in terms of the training they've missed and other opportunities. And so that is something that's being looked at. And finally, I'll leave you with this message. I've talked about sustainability. I hope I've imparted that sustainability is an extremely important role that nuclear plays. It's not just about doing less harm, it's doing about more good. So it's being able to provide clean drinking water and allowing hospitals to run 24/7, allowing modern technology within those hospitals, allowing access to electricity so you can have lights that are on into the night so that you can read and you can have more education after the sun goes down and the work is done. Nuclear enables this. And that is the message I wanted to leave with you today. Thank you very much. And now we can take some questions.
Thank you so much, Dr. Jeremy, for that insightful lecture. We'll now open the floor for questions. So we have the first question that comes from Gyane. He's from Saudi Arabia. He says, for countries building their first nuclear power plant, what is the single most important decision to get right at the very beginning? And what is one mistake that you hope they avoid?
So the infrastructure is the most important thing. Often when countries are looking at technology, they will be looking at the type of technology, the type of reactors that are out there, but you need the infrastructure in place to start, and the infrastructure has to be sound and robust and resilient, and it has to be there years in advance of any technology choice. And that includes the non-proliferation aspects, but the safety and the security infrastructure and the communication infrastructure. And this is part of the Milestones program. It's what it encourages as well, the IEA. I would say a single biggest mistake is, I touched on this, is not thinking that communicating with the public, thinking that we'll try and get the technology down, and then when the time comes, we'll talk about how we can communicate with the public. And this is the mistake that the rest of the world made decades ago and learned the hard way, that you need to have the public and the indigenous groups, all the demographic groups need to be in the tent talking about the technology and learning about it so that they can go out and be ambassadors of the technology themselves. And so I would encourage that to be thought of as something just as important as, well, it's part of the infrastructure, but just as important as the technology.
Okay, thank you so much, Doctor. The next question is from Yosef from Ethiopia. He says, given the long construction times of nuclear power plants, do you think nuclear can act quickly enough compared to renewables like wind and solar to address the global climate crisis and rapid energy expansion?
That's a great question. Nuclear does have this challenge. It does take much longer to build one. A lot of that is the public interaction. I know in Canada there's an extra 10 years just in interacting with the public and getting the appropriate approvals in place, and each of the approvals takes a lot of public interaction because the public has an opportunity to engage. So this is a challenge, and not just renewables, but you can build a combined cycle gas station in 3 years in Canada. You can build those right next to a city and people don't seem to care. But you try, so that's 3 years from thinking you want to build one to having it generating electricity. In 3 years in nuclear, you're still putting together the arguments to go through the processes to get the approvals. So that is a big challenge. you can address those challenges by speeding up that process. And I know in Canada, at least there, but also elsewhere, we're looking at cutting that time to achieve the approvals down by half, which will help. But you'll always be able to build other technologies quicker. And so it's a question of getting the message out there that it takes a little bit longer, but the technology that's going to be in place is going to be one that's able to provide 24/7 power. It's not going to be reliant on the weather, and it's not going to be reliant on backup power. And that backup power, unless you're going to have megawatt, gigawatt size batteries, which have their own environmental challenges, it's going to be fossil-fired technology. And so there's an understanding level there that you need to address, that it's not renewables by themselves that you're building in the short time. It's the fact that you're going to also have these fossil stations. Often, the more dependent you are on the temporary power that you get from renewables, that often it's a megawatt for megawatt. You need, for every megawatt of wind, you need a megawatt of natural gas to back it up, which has to be in spinning reserve waiting to go, because you can't have, for a stable system, you can't have a drop of a power supply. And so spinning reserve means you're actually operating the fossil station at the same time. I hope that answered the question.
Thank you, Doctor. We'll take one last question because of our time. This one is from Johnson Masego from South Africa. He says, on the NPT, why is that the pillar disarmament is hardly practiced? And why is that instead of disarming the 5 authorized nuclear states, they continue to modernize and expand their nuclear capabilities?
That's a fantastic question too. So the NPT does have this pillar of disarmament. It's not just about peaceful use of nuclear technology, but also the part of the bargain is that the countries that have the nuclear weapons, the 5 countries in the NPT that have the nuclear weapons recognized, need to do something about disarmament. And that's the part of the NPT. It's a very successful treaty, but the disarmament part is the least successful of those parts. And so this is a big disparity. So you're correct to point this out. The problem is that countries that have the nuclear weapons also control most of the nuclear technology, which is that's at the root of the challenge of coming up with an international treaty like this. So you needed to have that aspect in the treaty for the rest of the world to sign on to the treaty. But the countries that have the nuclear weapons, whether or not they're going to disarm, is controlled by a huge number of other factors. And the NPT by itself is not a disarmament mechanism. It's only a treaty saying that disarmament is a good idea and you should be doing something about it. So the NPT by itself can't encourage disarmament. It can only say that it is something that the countries are agreeing to do, and then we have to work at that aspect through other mechanisms.
Thank you so much, Doctor. We've come to the end of our Q&A session and our first session. On behalf of Newcomers for Nuclear Global, would like to extend our sincere thanks to you, Dr. Jeremy, for the truly insightful lecture. And to all participants, thank you for your engagement and your excellent questions today. Our next session will start in the next 10 minutes. We'll have a 10-minute break. Thank you so much, and we look forward to seeing you again. Thank you and goodbye for now.
Thank you. Enjoy the rest of the course. Bye-bye.
Thank you very much, Dr. Jeremy. If you can drop your email to connect with participants or your LinkedIn account, that they keep in touch with you. So we really appreciate your time and Nomagugu's also intervention. Thank you. Have a very good rest of your day there. Hello, Patrick. How are you doing? I can see you there.
Hi, Florencia. Good to see you as well.
Good to see you too. Do you want to have like a quick dry run that we can see your slides?
Sure, that'd be great.
Okay, let me just stop sharing. Thank you for making this time. What time is it in Bolivia now?
Well, I'm actually in the UK. I'm in Cambridge.
You're now in Cambridge. I thought that you were in Bolivia. Sorry.
No, I'm just visiting. Oh,
Okay,
there we go.
perfect. So Rafaella Binetti from Italy, she will be your moderator. She's also in the room.
Okay, great.
Hello.
Hello,
Hi.
Rafaella.
Hi, Rafaela.
Hi.
Good morning. How's everything? Thank you for making this time available. So now the participants are having 10 minutes break, but we will resume like very soon, 10 minutes actually. So you have also all the materials on the drive, the presentation, sorry, the bio for Patrick, so you can read it.
Yes.
Lanssina will be introducing you, Rafaela, and you also have some backup questions, but you can see that we're having tons of questions from participants. So they are having like lots of engagements.
Yes.
Definitely. We are reaching mostly like around 300, more than 300 people in the room. So this is really
Wow.
great, actually.
Wonderful.
So the recording will be available after today's session on the YouTube channel. You will be also able to share on your social media anything that you want to share about the school. Please feel free to do it.
Great.
Okay, I can see. Do you want to do it like full screen mode, Patrick? Rafaela, do you have any comments, questions before we get into your session?
No, thank you. Everything's clear.
Okay, perfect. And thank you for making this time available. We really appreciate your support.
Thank you.
Is this better?
A little bit, yeah. I think you just go around with presentation mode, and we will be able to see it soon, I guess.
Well, I am on presentation mode, so I'm surprised why that's not working.
Let's see. What if we return to the PDF in Adobe and then we do Control L, probably?
Let me slide only, and then I can make change this to. I think that's the best.
Yes, that's better to view. That's perfect. Thank you, Patrick.
Awesome.
You can keep it there. Don't worry, it's okay.
No, I can get rid of it. I'm just waiting, so I'll turn my camera on when we start, and then I'll minimize it.
No problem at all. Thank you, Patrick.
Awesome. See you guys in a bit.
See you soon. Thank you so much. Hi everyone. We're returning now from the break. So please take your best seat, grab your coffee, grab your tea, or any drink that you're taking. If you're having lunchtime, please enjoy your meal. If you're enjoying breakfast, please enjoy also your meal as well. Or if you're joining us from Asia, probably you are about to have like dinner time. So we will start very soon, just maybe in a minute. And please keep your mics muted that the speakers and the moderator can listen to the questions, to the comments, and the speaker can run the lecture appropriately. If you're experiencing some challenges, you can drop any comments on the chat. We also have the Q&A session available at the top of your screen. So feel free to utilize that area and space as well. Probably, Patrick, if you just allow me to share the cover slide that we have prepared for you and Rafaella, that'll be fantastic. Thank you. Oh, great haircut.
Oh, hi.
Hi. Okay, perfect. Let me just. So, yes, I think Lanssina is back. He will introducing you, Rafaella. So let me just get back to the cover slide.
Okay.
Perfect. So Lanssina will be introducing you, Rafaella, that the participants can get to know you more. So please, Lanssina, over to you, and the floor will be yours on Rafaella and Patrick. Thank you. Lanssina, can you hear me? I think he's having some challenges, so just a minute. Let me check your materials, Rafaella.
I'm so sorry, Florencia, can we go ahead? I have a case loss of connection.
Yes, sure. I'm just getting her bio ready.
Okay, thanks so much.
Thanks to you. Apologies for the delay. Sorry. So, dear participants, today we are running also the second session, Applying Nuclear Physics, Core Principles for the Modern Nuclear Workforce. And today I would like to introduce our moderator for today's lecture. We have in the house Rafaella Binetti, is a chemist and nuclear engineer currently completing her master's in science in nuclear engineering at Politecnico di Milano on the nuclear systems physics track. After a bachelor's in science in chemistry, she is a recipient of the IAEA Marie Skłodowska-Curie Fellowship, which supports women in the nuclear science and technology. She recently served as a young generation panelist at the OECD NEA China Forum on innovation in the nuclear back end, and took part in the Nuclear Politics Summer School organized by the Soka Institute for Global Solutions at Soka University of America. Alongside her studies, she's co-founder and CEO of RVV Aquatech, a startup developing sorption-based atmospheric water harvesting powered by low-grade industrial waste heat. So please, Rafaella, it's a great honor to have you with us in the house, and we really thank you for your time and great support. The floor is yours. Thank you.
Thank you. Thank you so much. And hello, everyone. And it's a real pleasure to open the session on applied nuclear physics. And our speaker today is Dr. Patrick Carter-Cortez, a nuclear engineering researcher who completed his doctoral training at the University of Cambridge. His work spans neutronics, thermal hydraulics, fuel behavior, optimization, and nuclear data applied to advanced systems. So essentially the full toolkit behind how a modern reactor is understood and designed. And alongside his research, he has worked as a subject matter expert for artificial intelligence companies focusing on CBRN risk and dual-use technologies. That's a combination I found particularly relevant for this audience. The technical fundamentals on one side and the questions on how those fundamentals intersect with security and emerging technology on the other. Patrick, thank you for joining us, and the floor is yours.
Thank you so much, Rafaella. And thank you so much to everyone who's joining today. Thank you for taking the time to listen to my slides. So to get started, I'm just going to complement a little bit the introduction that we received. I'm a physicist by training. My background was looking at different parts of physics. I quite enjoyed quantum mechanics, quite enjoyed shock physics. But while I was doing my master's in security science, I really gravitated towards nuclear, and that's how I ended up on this specific path. My research interests, as mentioned, span the whole gambit of what it means to be a nuclear engineer. I do neutronics, thermohydraulics, fuel performance. But what I'm really interested in is getting the ideas from paper to reality. And what I mean by that is there are many reactors currently in development, but they will need a whole host of experiments to be able to qualify the different components. And doing those in a way that's both cost-effective and safe interests me a lot. So if you have any questions about that in future, do let me know. So to get started with the contents of today, I'm breezing through because there's a lot to cover. What I want to do, the talk kind of is split into two parts. The whole point is to talk about nuclear physics and how it applies to nuclear engineering. So I'm taking the talk in the perspective of the nucleus, and then talking about the same kind of concepts, but from the perspective of the neutron, okay? And then hopefully at some point in your minds, there will be a connection between the two. But just as a short reminder, I can hear a little bit of noise, so please make sure you are all on mute. So let's get started. A little refresher from high school or chemistry from previous years that you may have studied. Everything is made out of atoms, and the atoms at the very center have a nucleus, and this nucleus is made out of protons and neutrons. Protons have a positive charge, neutrons have no charge, and these are surrounded by shells of orbiting electrons which have a negative charge. Now, the scale, I think, is very hard to fathom. On this diagram, for example, it would seem like the electrons are quite close, but if we look at the scales, there's 5 orders of magnitude between the atom and the nucleus. If we imagined an atom to be the size of a football stadium, for example, the nucleus would be the size of a coin in the middle of the football stadium. So the distance, the scale of difference between the atom and the nucleus is quite different. And when we're talking about nuclear physics, we're talking about those very, very small interactions that are happening in very small spaces known as the nucleus. And in fact, as many of you may know, most of the atom is just empty space, precisely because of these scale differences. How do we classify nuclei? Well, they have protons and neutrons, as we've spoken, and these are collectively known as nucleons. And depending on the number of protons, the number of neutrons, and the atomic mass number, they will have different properties. So many of you have probably seen this kind of symbols on the right. C for carbon, which has 6 protons in red, and then 6 protons plus 6 neutrons gives 12 nucleons, also known as the atomic mass number, which is there in pink. And throughout the lecture, I will try to keep using these colors so you know that A is in pink, nucleon number, Z is in red for protons. So a bit more information about what this all means. The nuclear reactions are determined by the protons and the nucleons present. So Z, the number of protons, really determines the chemical reactions that you're going to experience or be able to cause. Nuclei with different atomic numbers but the same proton numbers are called isotopes. For example, here you've got 3 different types of hydrogen. They're all hydrogen because they have 1 proton, but they have different number of neutrons, and therefore they have different masses and slightly different nuclear reactions, which is what we're interested in. Any kind of nuclear reaction is going to have these 4 things: conservation of charge, conservation of nucleon number, which is the number of neutrons and the number of protons, but not individually, rather the total. That's why we say conservation of nucleon number. Conservation of mass energy. And notice here that I haven't listed them as two separate things, but rather as one thing. We're going to talk about that a little bit more later. And finally, conservation of momentum. Now, when I say momentum, I do mean that in the classical sense of if I have two bodies colliding, there will be conservation of momentum, but I'm also alluding to quantum mechanical momentum, which we can consider as spin. And in general, a nuclear reaction is going to have this form, A plus B goes to C plus D, which is very important. So here, for example, I've written an equation using that form. So I've got a helium nucleus colliding with a lithium nucleus, producing a beryllium nucleus and a hydrogen nucleus. Now, strictly speaking, what's happening is the helium and the lithium combine to produce boron. But this boron is not in a stable state, hence why it has that asterisk. And so it decays very quickly into the beryllium and hydrogen. In practice, we don't write this intermediate step because it happens so quickly. However, that is strictly what's happening. And also, it is possible to write the same equation in the notation that you see at the bottom, though this is more typical of particle physics rather than nuclear physics. As you can see in red, the helium atom is the same as an alpha particle. That's why it's written as an alpha. And a nucleus of hydrogen is essentially just a proton, right? There are no neutrons. So it can be written with a P for proton. Now, why are we interested in this? Well, chemical reactions, which is, combustion, very simple, classic example, have energy releases in the order of 1 electron volt, right? We're going to talk about that unit a bit later, but what interests me for this concept, for this slide, is the order of magnitude. When we talk about nuclear reactions, the energy release is much, much greater. It's 10 million, on the order of 10 million electron volts, and even higher. So we're talking about 6 or more order of magnitude more energy release. And in fact, the energy release is so big in a nuclear reaction that we can measure an associated change in mass. So if I have a nucleus and I measure its mass, it will have less mass than the sum of the individual components. What I mean here is a nucleus is made of neutrons and protons, but if I had, for example, 5 neutrons and 5 protons, if I took the mass of 5 protons and 5 neutrons, it wouldn't be the same, it would be less. And the question is why? Well, let's think again about what's happening. We said that the nucleus is a very, very, very small thing. The diameter was times 10 to the minus 15, right? And inside the nucleus, we have protons with a positive charge and neutrons with no charge. So we're packing in a lot of positive charged neutrons into a very, very small space. Now, many of you will probably know from your background in physics of Coulomb's law. Coulomb's law tells us that if we have two like charges, they're going to have a repulsive force. So, and that is proportional to the inverse of the square of the distance between them. So if I've got, hypothetically, 2 protons at the very edge of the nucleus, 10 to the minus 15, the force that they're going to experience is on the order of times 10 to the 30 newtons. So that's a huge, very big force of repulsion. These protons do not want to be together. So what's happening? Well, if I'm going to keep these protons that don't want to be together in such a small space, I need some sort of glue. And it turns out that the energy to keep these protons together comes from the defect or the lost mass, if you want to look at it that way, from here. So here we've taken this inequality, made an inequality where we are subtracting this delta M, which is this, what we call the mass defect. Mass defect is equivalent to the binding energy, which is the energy or the glue, if you will, to keep everything close together in this tiny, tiny little space. Now, in practice, the formula would go like this. The mass of the nucleus is equal to N mass of neutrons plus Z mass of protons minus the mass defect or the glue required to keep everything together. And then we can rearrange the formula algebraically to calculate this mass defect. Now, strictly speaking, binding energy is the energy required to break a nucleus apart into its constituent nucleons. However, I think of it better as the what we need to keep everything together. It's kind of the negative or the inverse, but it's the same concept. And where does this equivalence between binding energy and mass defect come from? Well, it comes from this equation, which is probably the most famous equation, Einstein's equation, E equals mc squared. So I can see how the defect in mass, the mass that is lost, and I'm using air quotes because it's not lost, it's just becoming binding energy, is equivalent to the mass times the speed of light squared, and that is the binding energy. Now, in principle, this is very hard to measure. You know, we just said nuclei are inside atoms, and they're one small part of the atom. So it's not easy to measure the mass of a nucleus individually. Of course, it's possible, but you have to strip it of all the electrons, and it's not a trivial exercise to do. It's much, much more simpler to measure the mass of an atom and kind of compensate the fact that the mass of an atom is the mass of the nucleus plus the electrons. And then instead of taking the mass of a proton, taking the mass of a proton with electrons, also known as a hydrogen atom, and kind of calculate in that sense. So you can see how we went from having mass of a nucleus to become mass of an atom because we're adding the electrons, because that's easier to measure. And then we're compensating for that by, to the protons, adding the electrons that the hydrogen atom would have. And we get the same result. Well, not the same result, but very similar result, and something that's much more plausible to measure in real life. Some important units. Obviously, here we're talking about very, very small masses. So it doesn't really make sense to talk about kilograms. Rather, we use atomic mass units, which are defined as 1/12 of a mass of a carbon atom, and it is approximately 1.66 times 10 to the minus 27 kilograms. What I want you to remember is the times 10 to the minus 27 part. It's a very, very small amount of mass. So then looking back at the equation that we had here to calculate the mass defect, we can substitute in using atomic mass units, the mass of the nucleus, the mass of a hydrogen atom in lieu of a proton, and then the mass of the atom instead of the mass of the nucleus. Similarly, since we're talking about very small amounts of mass, it makes sense to have an energy unit for the very small amounts of energy that we're talking about on these atomic or rather nucleus scales. So dimensionally, we can see that E equals mc squared makes a lot of sense. You know, if you think of other sorts of energy, for example, kinetic energy, that's a half, which is unitless, mass, which is in kilograms, times velocity squared. So doing a dimensional analysis, we see that E equals mc squared makes a lot of sense. And if we're trying to figure out the energy that's related to one atomic mass unit, we see that the answer is times 10 to the minus 10 joules. So again, this is a very small amount of energy, so it makes sense to come up with a new unit known as the electron volt, which would literally taking the charge of an electron, multiplying it by the potential difference of 1 volt, and that becomes energy, which is times 10 to the minus 19. So it makes sense to use these units. Now, this is a key thing that I want you to remember. Since we don't talk about mass and energy as separate things, but rather as mass energy, to convert between one and the other, it's very useful to keep this shorthand in mind, where one atomic mass unit is equivalent to 931 mega electron volts. Okay, so we've spoken a little bit about the nucleus, spoken about some units, where this binding energy comes from, and now we can talk about nucleus and its stability. So this is a very important graph. As you can see, on the x-axis, we have the number of nucleons in the nucleus, aka how big is this nucleus. And then on the vertical axis, we have the average binding energy per nucleon. So it makes sense that if I have 2 protons in the nucleus, I will need a certain amount of binding energy to keep them in this very small space. I'll need some amount of glue. But if I have, 90 protons in a nucleus, I will have to have more glue to keep more protons together. However, just because I have more glue, more binding energy, it doesn't mean that it is in its most stable form. It turns out that stability of the nucleus is determined by the average binding energy per nucleon. So we take the total amount of binding energy necessary to keep the protons together, and we divide it by the number of nucleons present. And it turns out that the maximum, the most stable nucleus is iron. So summarizing what I just said, as the number of nucleons increases, the mass defect increases, therefore the binding energy or the glue increases. However, that linear or rather proportional relationship isn't the case per nucleon, and in fact a curve forms, and nuclei want to be in the most stable form possible. Basically, everybody wants to be iron. And how does this happen? Well, the heavier nuclei, like uranium, fission. They want to split up and become smaller, and the lighter nuclei want to become bigger, and so they fuse together to become iron. This is just fission and fusion. There are other processes as well that can happen, which we'll talk about in a second. Before I do that, however, I want to point out certain anomalies, as it were, to this curve. As you can see quite clearly, hydrogen 4 is significantly above lithium 6 or 7. And similarly, carbon 12 is slightly higher than would be expected, and the same with oxygen. Now, why does this happen? Well, without getting into it too deeply, basically there's a thing called magic numbers, where nuclei, like electrons, have certain energy shells, and there's certain energy shells that are more energetically favorable. And so what you're seeing is this effect in practice. It's a quantum mechanical effect. I don't want to go into too much detail about that. It's more to point out this interesting anomaly. And it makes sense a little bit because nature loves symmetry. So it is not surprising that the most stable combination, i.e. the one with the most stable isotopes, is having an even number of protons and an even number of neutrons. And in fact, having an odd number of protons and an odd number of neutrons is very, very rare. There are only 4 stable isotopes that behave in that way. So as I said, everybody wants to be iron. So fission happens for the heavy isotopes. Fusion happens for the lighter isotopes. But there are other types of processes by which nuclei can become more stable. And you can see in this chart, there's beta positive or positron in orange, beta negative release, alpha decays, proton emissions, neutron emissions. These are all different processes that nuclei can undergo in order to become more stable. Okay, so now we're going to look at some of these radioactive decays. So what do we mean by radioactive decay? Well, we have a nucleus, but it wants to be in its most stable configuration possible. So what this means is that a process is going to happen by which some of the nuclear binding energy will be released, such that the nuclear binding energy per nucleon is going to improve. And in all these processes, like with any nuclear reaction, mass energy, momentum, electric charge are conserved. Radioactive decay is spontaneous and stochastic, which means that nothing can be done to help induce or accelerate the decay of a particular nucleus. It just happens on its own. And stochastic means that if I have 100 or n identical nuclei, we can't predict with certainty which one will be the next to decay. So the individual behavior of nuclei is random. However, it is still a probabilistic process. And what this means is that even if I cannot tell you the specific nucleus which will decay next, I can tell you something about the macro behavior, i.e. I can tell you how many nuclei I expect to decay within a certain given period of time, because these things are governed by probabilities. So let's look at some of the examples of the radioactive decay that happen. Well, the most classic example is radioactive decay via the emission of a gamma photon. Any nucleus is capable of undergoing this. Now, as you can see on the left of the equation, we have cobalt with an asterisk. This asterisk shows that it is not in its ground state, it's in an excited state, meaning it has excess energy. And so the simplest way that it can get rid of this excess energy is to emit a photon, a gamma photon, that has that energy, such that the cobalt nucleus decays into its ground state, where it is in fact stable. So that is the simplest form of decay. Another example is alpha decay. In an alpha decay, there is an alpha particle or a helium nucleus, they are the same thing, that's being emitted, and some photons of gamma are also emitted in the process. Now, in order for this to happen, there has to be normally a heavy isotope, okay? Because basically what you're doing is you're overcoming, there are quantum wells, potential wells, and you're overcoming that energy in order to emit this particle. So this typically only can happen with big nuclei. And in this case, the emission is monoenergetic, about 4 to 6 mega electron volts. Another decay is the beta decay, where cobalt 60, for example, becomes nickel 60. It emits a beta particle, also known as an electron. It emits a photon, and it emits an antineutrino. The antineutrino is that letter nu with the bar on top of it. Now, this stumped many physicists for a lot of time because unlike the alpha particle emission, the beta energy was a continuous spectrum. And that didn't make sense because, you know, from the perspective of the conservation of momentum, we thought that like alpha, it would have to be a determined amount of energy that was being released. However, Pauli and others hypothesized the existence of a neutrino, which is well, a very, very light, if not massless, particle that what it does is it takes away spin. And so that was very comforting to physicists when this particle was finally able to be detected. They're not easy to detect because they don't like to interact with matter, which we'll talk about a little bit more later, but just to keep that in mind. Now, the opposite reaction is also possible, where instead of emitting an electron, we're emitting an anti-electron, also known as a positron. And in this case, instead of emitting an antineutrino, we're emitting a neutrino. Okay, so this is very interesting because it's kind of the exact opposite of what's happening with the beta decay. Now, as a quick aside, the reason why when we talk about protecting from radiation, we don't typically think of beta positive as something that we need to protect from. That is because positrons are very short-lived in that they will annihilate with electrons which are found in nature and emit to gamma rays. Now, this is a very interesting reaction known as the electron-positron annihilation because the entirety of the mass of the positron and the electron becomes energy. So on the left-hand side of this equation, we've got two particles, and on the right-hand side, we've got two photons. So this is a total conversion from mass to energy, and each gamma ray has 511 kilo electron volts, which is equivalent to the mass of these particles in the first place. On this slide, we have the only time where electrons are mentioned, because what happens in a K capture, which is another form of decay, is one of the electrons in the K shell. So the K shell is the one nearest to the nucleus, and typically it contains two electrons. One of these electrons will go into the nucleus, it will be absorbed by the nucleus, and therefore there will be changes to the nucleus. It will no longer be germanium, but rather will become gallium, and it will emit a photon and a neutrino in the process. Now, what happens is there becomes a hole in the K shell, so an electron from another shell decays into the K shell, and that's what emits the gamma photon. So this is a very interesting reaction where we see electrons taking part in a nuclear reaction. And this is, again, a radioactive decay, meaning that it is spontaneous, it is stochastic, and it is probabilistic as well. As a quick summary of where this is coming from, gamma decay is a quantum effect, alpha decay is a quantum tunneling effect, beta decay, beta positive decay, and K capture are weak interactions. So they have different physical backgrounds, so to speak. Now, the beta and the beta positive and the K capture all change the proton number, and alpha also changes the proton number, but it also changes the nucleon number, because remember, we're extracting a helium-4 out. So the total number of nucleons will also change. And the gamma decay is the only one where nothing is changed. All that's changed is that the excess energy is removed in the form of a photon. Now, even though we've spoken about all these different types of radioactive decays, when it comes to ionizing radiation, we only really have to think about alpha, beta, and gamma. Here, for example, in the K capture, what's produced? Gamma. Here, gamma. Here, gamma and beta. Here, alpha and gamma. So the thing that concerns people when it comes to radiations emitted, it's alpha, beta, and gamma. Now, alpha in and of itself isn't too worrying because it can be stopped by a thin layer of paper. So unless you ingest it or inhale it, and it's very easy to protect from. Beta particles, on the other hand, have a bit more energy. They have a bit less ionizing power. However, they can penetrate deeper and therefore are more of a risk to humans. And gamma photons, well, they have very low ionizing power, they have high energy, and so they can travel through most materials, and you need quite a bit of lead or cement to be able to stop them. So that is where most of the risk is. Now, because we said that radioactive decay is probabilistic, we are able to make certain predictions about the total behavior of a sample instead of individual nuclei. And so observations have led to the decay rate or the radioactive decay law, where we know that the decay rate is proportional to the number of radioactive atoms present. And this constant of proportionality, the decay constant, is in fact an intrinsic property of the isotope. So it doesn't depend on temperature, it doesn't depend on external conditions, it simply depends on how much of the isotope, or rather which isotope I have. And then using first order differential equation solving, we can come up with an equation of how the population of radioactive atoms will change as a function of time. And it turns out to be an exponential decay, as you can see in this graph. Now, we can't easily count the number of nuclei, or in fact, we can't even count number of atoms very easily. So in fact, what we do more frequently is measure the mass. And so the mass of a sample will decay in the same way. And so we can use Avogadro's constant to make an equivalence between mass and the number of nuclei. Now, a key property of radioactive decay is that in certain intervals, the mass will decrease in a predictable way. So 40 to 20 takes about 8 days. 20 to 10 takes another 8 days. 10 to 5 takes another 8 days, and so on and so forth. So this half-life is also an intrinsic property, and it's related to the decay constant by the equation that we can see on the screen. Now, a quick note here is oftentimes we can measure activity, which is how many decays are happening per second, using a Geiger counter, okay? However, big caveat and a big warning, if you don't learn anything else in this lecture, let it be this. Activity alone does not tell you which type of radioactive decay is occurring. If you see a lot of videos of people going to Chernobyl or other sites and they have a Geiger counter that's beeping like crazy, that doesn't in and of itself correspond to a harm or potential of harm. Because as we mentioned, alpha particles, unless you ingest them, are not a health risk. So I could have a Geiger counter and point it at an alpha source and it will go sounding like crazy, but that doesn't mean that it is in and of itself a human risk, okay? All a Geiger counter can do is count the number of times that an ionized gas atom has reached the anode. And therefore, it doesn't tell you what is causing this ionization. So that's something to keep very in mind. Oftentimes, when a nucleus decays into something more stable, it can undergo a second decay. So it's a chain rather than a one-off thing. So imagine you have isotope A decays into isotope B, and isotope B is also radioactive. It hasn't fully reached a stable state, so it wants to go on and produce another decay. Now, Depending on the properties of the half-lives or the decay constants of these isotopes, you will see different behavior. So here on the right, I have 3 graphs. Now, I want to point out that the graph in the black line is exactly the same for all 3, because that is the decay of A, the first initial isotope, and that is governed by the equations that we just saw. The decay of B, however, also depends on the birth rate of B, if that makes sense. So A decays into B, and once B is produced, it can decay into C. So depending if B decays faster than A, or if A decays faster than B, you will see different effects. For example, here in case A, we see that isotope A, has 5 times the half-life of B. And what that means is that after a certain time, the saturation activity is reached where both of them are basically at the same population. Now, if the reverse were true, that the half-life of B were much smaller than the half-life of A, which is the case we've got here on the right, top right, you see this sort of saturating effect that happens because B is not able to decay fast enough. And then the intermediate case is the one here in between the two. So we can tell a lot about the sequence and the half-lives of the isotopes depending on how they progress as a function of time. So we've spoken about all the different types of radioactive decay. Now we're going to talk about fission from the perspective of the nucleus, which is what we're most interested in as nuclear engineers or professionals in nuclear engineering. So what happens? Well, unlike the other cases that we just saw, which were spontaneous, probabilistic, where the nucleus in and of itself, it wanted to do something, for fission to begin, the target nucleus has to absorb a neutron. So this neutron is not coming from the nucleus itself, it's coming from outside. So this isn't something that happens in and of itself, it's something that happens because a neutron comes in to cause the fission. The fission will have a binding energy of around 7 to 8 mega electron volts, which means that the target neutron, after it's absorbed the neutron, the target nucleus, after it absorbs the neutron, will have excess binding energy. Therefore, it's not going to be in its stable state, and it needs to do something. Now, many things it could do, but one of the things it can do is fission. And this happens really quickly. We're talking times 10 to the minus 8 seconds. And fissioning literally means the splitting up. So imagine you grabbed a book and you break it in half really quickly. That is kind of what's happening with fission. You're splitting it randomly into 2 similar sized parts. So what you produce, here's an equation, for example. I've got a uranium-235 nucleus. It absorbs a neutron, and then it splits into 2 fission products that here we have in blue, lanthanum and bromine, and it also releases between 0 and 5 neutrons, shown there in red, 2 in the equation. Now, this is the key thing. It only produces 2 fission products, never 3, never 1, always 2. And it comes back to my idea of a book, right? Like if I have a book and I grab it in by 2 and I split it, it's going to produce two parts. And that's why you only have 2 fission products. If we look on the right, we can see kind of the distribution of the 2 fission products. And it's very interesting, you know, if I have 235 nucleons in the uranium atom and I absorb a neutron, then I have 236. That's an even number. 236 could be split into 2. However, coming back to my book analogy, if I'm, you know, anxious and I grab a book and I just split it in half, what's the probability that it will split exactly in 2 parts that are exactly the same size? Very little. So in fact, what happens is you see this range between 90 and 110, 105, and 125 and 145, that kind of distribution, and very little here where it would be exactly in the middle. So think about, you know, this violent splitting of a book into 2. What are the odds that both sides would have the exact same number of pages? Very, very low. Now, most fission products will be radioactive, okay? So here, for example, bromine and lanthanum, they will have radioactive decays, and depending on the half-lives of the isotope, it may have several others, right? So here, for example, we have xenon, which is a fairly common fission product, which decays into cesium, barium, lanthanum, and celerium. So that's the kind of sequence that's happening. And normally, but not always. Earlier in the decay chain, you tend to have isotopes with shorter half-lives, but that's not necessarily the case. And there will be this sequence of decay. So fission happens, randomly split the book into two fission products. These still have excess energy. They're not in their most stable form usually, and they will have beta and gamma decays into something more stable eventually. Now, what this means is that a fission reaction releases around 210 mega electron volts of energy, okay? This is a lot of energy, and it doesn't depend on the energy of the incident neutron. So this is a property of the nucleus that is being fissioned. Now, in this table, we can see where this energy is going. Some of that energy is, well, not some, a lot of that energy, 168 out of 212, are the fission products. So there's two big isotopes that I produced. And then some of that energy is also the fission neutrons produced. Remember, we're also producing 0 to 5 neutrons. Now, there's also going to be some fission gammas released. That's about 7 mega electron volts. And then the rest from then onwards, it's to do with the fission products. So the fission products, remember, are often not stable. So they will decay by beta emission. They will decay by gamma emission. Remember that betas, when they decay, they emit neutrinos. So we're going to have some neutrino energy. And also there can be some captures of gammas, which is a very small amount. So this is where the energy is going. Now, of all this energy, the neutrino energy is not harnessable. It's not recoverable. Neutrinos do not like to interact with anything. That's why it took so long for us to even measure them and discover that they did in fact exist. So that is the energy that's lost, and I'm using air quotes because it's not lost, but it's not something that we can recover and use in a nuclear reactor. So those neutrinos just continue on to the universe. But everything else is going to be captured, deposited in different parts of the reactor, which can be harnessed in a beneficial way. A key thing here, though, is that approximately 8% of this recoverable energy, so excluding the neutrinos, will be due to the beta decay of the fission products and the gamma emissions of the decay of the fission products as well. What this means is that after I shut down a reactor, what you've done is you've shut down the fission. You're not going to produce any more fission products. But the fission products that were already in the reactor and are decaying, those are going to continue. Why? Because decay is spontaneous, stochastic, and probabilistic. I can't stop. I can't speed up, and I can't stop decay. So what this means... Sorry, I've got someone speaking. Please mute yourselves. So the decay is happening all the time, even if I shut down the reactor. Thank you. And this is a problem because the heat that is produced by these decays will continue, as we can see in this graph, for hours, days, weeks, months, years even. So in Fukushima, for example, the reactor was successfully shut down, but obviously the fission products that are there were still decaying. They were still producing heat, roughly 8% of the heat of the reactor, and that is what caused a little bit of damage to the core. And that's where it comes from. So it's very important to keep in mind what you can control and what you can't control. So to sum up a little bit of fission from the perspective of the nucleus, fission requires this neutron to come in and initiate the reaction. Therefore, it's not spontaneous and it is controllable. If I put in nuclei, I can make the thing happen. If I take away neutrons, I can make it stop. So fission is a controllable thing. And the other thing is that fission produces more neutrons, which means that those neutrons can then be used to produce other fissions and thus sustain a chain reaction. And that leads me to the second part of this talk, which for time reasons, I'm going to go even faster. It's the interaction of neutrons with matter. So now we're looking at the same story, but from the perspective of the neutron rather than the nucleus. So there are two ways that a neutron can interact with matter, with a nucleus. One is the neutron comes into the nucleus and it is absorbed and it produces this excited nucleus, as we can see on the left. On the right-hand side, we have we don't form a compound nucleus, and we can imagine like two balls just colliding and going in different directions with different momentum. So these are the two big ways that neutrons can interact with matter. Let's start with the second, the one where we have two balls just colliding with each other. The way this is described is elastic potential scattering. Literally, the neutron scatters or bounces off of the nucleus, and we call it elastic because kinetic energy, momentum are conserved. Here, we are not changing the excited level of the nucleus. It stays in its ground state throughout. The only thing that happens is the transfer of kinetic energy between the nucleus and the neutron. Now, in a head-on collision, the neutron loses most of its energy. If it were at an angle, it would lose less. Similarly, if the neutron has a similar mass as the nucleus it's colliding with, it will lose a lot more of its energy. A way of thinking about this is, imagine you have a tennis ball, okay, and you hit it against a brick wall. Now, the brick wall has a lot of mass, so that means that the tennis ball is going to bounce back with almost all of its energy, right? Like, it's not going to lose much of its energy, and the brick wall is not going to change a lot. However, I've got two billiard balls which have similar masses, and they collide. Well, it's possible that one of them will, the one coming in, will lose its energy, and the other one will move. You know, so these are analogies to help explain why in a head-on collision, a neutron loses most of its energy with a small nucleus rather than a large one. And this is the reason why in nuclear reactors, when we talk about moderating or slowing down neutrons, the way to do it is with water, for example, which has many hydrogen atoms. They have similar masses to a neutron, and therefore on a collision, elastic potential scattering, the neutron will lose a lot of its energy. Now, looking at the second type of interaction, the compound nucleus formation, there are many kinds.
Patrick,
Yes.
I'm sorry to interrupt you, but you have 2 minutes to wrap up. I'm sorry.
Okay. That's okay, no worries. So the compound nucleus formation starts with the neutron being absorbed by the nucleus. It forms an excited state, and then it can decay in several ways. So one of the ways that it can lose this excess energy is producing a gamma photon, which we saw before. Another way would be to emit an alpha particle, which we can see in this example. It can do inelastic scattering, where it becomes a compound nucleus and then it releases the neutron again. So the before and the after look very similar. The only difference is that the nucleus ends up in an excited state, which then decays by emitting a gamma. Or the compound elastic scattering, where the before and the after look identical. However, in the middle, there's a step where the nucleus was absorbed by the nucleus. The neutron was absorbed by the nucleus. Now, this is obviously indistinguishable from elastic potential scattering. So in practice, we only talk about this as both of them together as elastic scattering. But the mechanism is very different. Briefly, the fission depends on the energy of the neutron. We spoke about how it's a controllable process. So depending on the energy of the neutron, we can determine if fission will happen or not. However, the energy released by the fission is independent of the energy of the neutron. I made this distinction here at the top. We have the fissile atoms, which are naturally occurring in nature. And then at the bottom, we have artificially produced nuclei, which can be fissile. Here are some definitions that you can check later. I think the thing that I want to finish with, there's a lot of information here, but I think the thing I want to finish with is this graph here, which kind of explains why reactors happen in the way that they happen. So you see that the probability of a reaction is much higher at lower energies than at higher energies, which is why most reactors on Earth are thermal, and they have water-based moderation where these neutrons are being scattered with hydrogen in the water to lose energy and thus make fission more likely. In the interest of time, I'll end there and open up to any questions.
So thank you, Patrick, for your lecture. It was excellent, and everybody is loving how you teach things. And now we have some questions. I collected some of them from the chat. And for instance, we have from Luwine, if radioactive decay is spontaneous and cannot be induced for a particular nucleus, why do some nuclei remain stable while others are inherently unstable? What determines that difference?
So the stability is determined by the binding energy, or the glue, per nucleon. So all atoms have different amounts of binding energy in them. Some of them have excess energy, and therefore what they're trying to do is come up with a ratio that is most stable. Simply put, it's like everyone's trying to become iron, right? That's a very simplified explanation, but that is ultimately what determines stability. It's the average binding energy per nucleon.
Okay, thank you. And there's also another question from Amaton Albert. And the question is, why do we need fast neutrons to fission U-238, but thermal neutron for uranium-235?
Right. So the reason, the underlying quantum mechanics behind it isn't very simple. But let's see if I can find the graph. So in this graph, you can see uranium-238. Its fission cross-section, which is the probability of a neutron inducing fission, is 0. Like the graph starts here at 1 mega electron volts. So this is an observation based on experiments. The underlying quantum mechanical explanation of why is not really suitable for this level. But the point is that the experiments we have show that the only energies at which uranium-235 will cause a fission is at this. However, even so, if you look at it, it's significantly lower. Like if we have uranium-235, which is in green here, this is like 1,000 times more likely than uranium-238 at 1. So really, the probability is still very low, which is why most reactors do not depend on the fissioning of uranium-238, but rather they depend on the fissioning of uranium-235, because uranium-235 fissions at any energy, but especially at lower energy.
Okay, thank you. And there's another question from Rolando. Have there been any research on speeding up the decay of radioactive waste?
So we cannot speed up the radioactive decay. Radioactive decay is spontaneous and stochastic. What people have done, however, is put waste in different forms. So in glass, for example, and so in a way what they're doing is they're playing with the shielding to therefore reduce the harm that could be posed at a certain distance or to people nearby. But to physically induce or speed up the decay of nuclei is not possible. And that's one of the reasons why it's so tricky, right? However, what can be done is you can change. So if I have a nucleus and it's radioactive, it will decay. But I can do things to it like add a neutron and it will become a different isotope. And maybe that isotope has a shorter half-life. So I can do other things to it. And this is the concept, for example, of a closed fuel cycle, where you have the fission, you've got certain amounts of fission, and then you have a radioactive high-level waste. But instead of removing it from the reactor, you try to make those things fission. So that's why in France, for example, they have different concerns regarding waste compared to places like the UK or the US, where they don't do that. They do shorter fuel cycles. So to make the radioactive thing go faster, not possible. To change that isotope into something else, either by making it fission or any other reaction, whatever be it relevant, and then that has a lower radioactivity, that is possible.
Okay, thank you. And I see that someone raised their hand. So, okay. Ezekiel?
Yes, thank you very much, Dr. Patrick. Lectures were very comprehensive. Thank you. Yeah, so from the beginning, you made a statement. You said getting the ideas from paper to reality, that is of much essence to you. And then when we look at fission, where we have a neutron splitting a uranium to produce lanthanum and bromine, I want to ask about the production of lanthanum. How is it relevant to reducing climate crisis with the production of lanthanum?
Well, that was just one example. Again, fissioning is the splitting of the book randomly. So it can produce lanthanum, it can produce xenon, it can produce many different isotopes. We don't really have a say or a way of determining or selecting which fission products are going to be made. So, lanthanum specifically isn't the objective. The objective is to get the fission, because the fission releases 210 mega electron volts of energy, of which roughly 200 can be harnessed and therefore used to heat up water, move a turbine, and produce electricity. So the fission products per se is not what's of interest for climate change. It's the energy that's released with any fission reaction and harnessing that to produce vapor and thus move turbines and produce electricity.
There's another question from Sarah. I see you raised a hand. Okay, raised by mistake. Then Halima. Halima, do you have a question? And Ezekiel, do you have another question?
Yes, I have another question.
Great.
Yeah, so atomic mass unit is equivalent to 931 mega electron volts, right? So I want to ask, what is the practical implication of this relationship? One atomic mass unit equals 931 mega electron volts. Like how do we make somebody who has no knowledge in this nuclear physics understand something like this practically?
Right. Well, it doesn't have a practical application in and of itself. What it does is that instead of, when we solve these kinds of problems, to calculate the binding energy of a certain nucleus, for example, it doesn't make sense to keep using, times 10 to the minus 27, because you'd be having 0.0000 too many, like it's not useful numbers. So really these units don't have a practical application per se. It's just the units that we use in this specific situation to make problems a lot more tractable and manageable to solve. But for example, the calculation of 210 mega electron volts being released by fission, that is a calculation that can be done using, if you calculate the mass of the uranium and the neutron, and then you calculate the mass of the fission products and everything on that side, you can calculate the energy that's being released. So that energy released, the calculation is based on the masses, and then you convert that into mega electron volts. So that's kind of the use. But 931 equals 1 atomic mass unit is just a mathematical tool. It's not a practical application in and of itself.
Okay, now we can take 2 more questions. There is Cheradi. Do you want to ask something?
Yeah. Well, thank you, sir. I just have one question. It's about the magical numbers. You show us there is 2, 6, 8, 14, 20, 38, but we learn that we don't learn that 6 and 14 and 38 is a magic numbers. So it's not clear for me. I want to ask you about that. And thank you.
Sure. So the whole concept of magic numbers really is a quantum mechanical thing. So basically, it's saying that certain combinations are more stable than other combinations. So the numbers that I put on my slide, 2, 6, 8, 14, 20, 30, 50, 82, and 126, they come from a textbook. There's nothing in and of themselves. But what we can tell from them is that they're all even, because nature really likes symmetry and it really likes even numbers. And that's something that we can empirically observe by the number of isotopes that have even number of protons and even number of neutrons. But why specifically those numbers? It's a quantum mechanical thing related to wave functions and probabilities that goes beyond the scope of nuclear engineering per se. But it's an observation that we notice.
And I think we have one more question from Gyane.
Yeah, thank you for the presentation. My question is about the cobalt, and it's only the gamma energy. I think it's from, I don't remember the number, to 10 keV. How we can measure this energy?
So the amount of energy deposited by a photon of gamma photon, well, the way that it's measured is using basically the principle is you have a plate and this plate absorbs this photon and then that causes some sort of current, and the proportionality of that current is proportional to the incident energy. So that's kind of how you measure signals from the gamma photons. It's not really my area of expertise. I'm not an instrumentalist. I don't really work with radiation in that sense. But that is the core principle. This energy, this photon is deposited, produces a current. That current is proportional to the size of the energy that it had. That, I believe, is the fun. But I actually don't know. That's not my area of expertise, the measuring of radiation.
Okay, Patrick, thank you very much for a really rich session, and thank you all for the question, and see you in 5 minutes for the next session.
Thank you so much.
Thank you, Patrick. Thank you, Rafaella, for your great opportunity of being here with us. We are very grateful for your all engagement in the program. So please, dear participants, you have a 5 minutes break while we resume for the next lecture to close the first day. Thank you very much for staying with us. Hello, Mr. Christophe. I'm Florencia from Mexico. I think you can hear me. If you can.
Hola, ¿cómo estás? Sí, te oímos.
Hola.
Y hablamos español también.
Ay, muchas gracias. Buena tarde por allá, ¿cómo están?
Muy bien. Y Beatriz es mexicana, como tú.
Sí, es un gran orgullo y un gran placer poder conectar con ella y conocernos en este espacio. Muchas gracias por su apoyo.
De nada. Bueno, ¿estamos listos?
Claro que sí. ¿Les gustaría compartir su pantalla para saber si no hay algún fallo o que todo esté bien la conexión?
Creo que sí, Beatriz lo va a hacer.
Ah, ok, perfecto. Se encuentra Beatriz, no la encuentro.
¿Beatriz está aquí?
La estoy buscando en el chat. Pero
Voy
no
a ir a ver en su lugar. I'll be right back.
Muchas gracias. Sí, claro que sí. Muchas gracias. Hi, Rebecca. How are you doing? Good evening. Many thanks for accepting to moderate this session.
It's good to be here. How are you?
Very good, thank you. Can we check your sound and camera? I think it's perfect.
Yes, I think so. You can see me, can't you?
Yes, perfectly. You have the package for this lecture. All the presenters of the bios, I mean, there for Beatriz and Mr. Christophe as well. And you have also backup questions, but you can see that we also are having a lot of interaction from participants. So feel free to utilize the information as you consider.
Okay, that's fine.
Perfect.
So, with the questions from participant, I think it would be good to take it after the speakers.
Yes.
After their speak, okay. And usually, how would they send me a message, or they would raise their hands, or I think.
Yeah. So
Yeah.
They will have 35 minutes to complete the lecture, probably a little bit more because we have 2 speakers in the house. We're closing. This is the last lecture of today. So in case that we exceed like 5 minutes time, we can also manage to recover that by the end of today's session. And we can give them a private message to remember them about the time constraint.
Okay.
Perfect.
That's fine. I think we should be. I saw the backup questions that you put in, but I put together a few questions before that. So
That's
I may want
perfect.
to. Okay.
That is perfect, and thank you so much. So feel free to utilize the information as you consider, and I think we will have a lot of interaction from participants.
Okay. Yes, that's fine. Thank you so much. So you said we start in 5, so I stand by.
Thank you so much, Beatriz.
Right.
Beatriz, buenas
Beatriz
tardes.
on? Okay.
Yes, everything is on. Maybe you can stay 1 minute more, Rebecca, that the speakers for today, they can know you. From NEA, Mr. Christophe and Beatriz. Rebecca will be today your moderator for your lecture.
Oh, great.
Nice to meet you,
you.
Mr. Christophe. Yes. I hope we have a very good interaction. Can you hear me?
Yes, I can hear you.
Right. Okay. So I was just saying that I hope we have a very good interaction, and I just hope that the participant will also have a few questions here and there, but then whichever ways, just feel free to the materials, even outside the materials, anything that is important for we as newcomers to learn from any area. We are willing and we are ready. I mean, that's the whole essence of this global summit. So I hope we have a good time.
I think so. I hope so too. Hope there are lots of questions.
Right. Thank you. So I think today's one, the lay people, I mean, a lot of you may be nuclear engineers, nuclear this, but I'm a lawyer who is into energy in general. So I think from the background I'm coming from, I'll be representing a lot of the lay men and women, people who are not really nuclear scientists per se. And I just want to hope that we'll have a very good time. Thank you. Right.
Thank you.
Hello, everyone. I'm already connected. I was having some technical problems, but I'm here.
Thank you so much, Beatriz. It's a great pleasure to have you with us today.
Thank you.
I think we can resume maybe in 1 minute. And I'm going to share the cover slides we have prepared for your talk. My colleague Lanssina will be introducing Rebecca. And Rebecca, after her introduction ends, she will be introducing you for you and for Christophe. Oh, apologies. I had a typo. Let me just correct it very quickly.
Can we start?
Yes, we can start, Lanssina. Please, dear participants, take your seats and let's go through the final day of today's lecture. Please, Lanssina, over to you. You can introduce Rebecca. Thank you.
Okay, thank you. Rebecca Ndlovu, lawyer, notary public governance professional. Yeah, it is more than 3 years I met Rebecca in Ghana, Accra. It was 3 days or 4 days amazing forum symposium in nuclear area. It was my first big meeting in person nuclear area. It was very nice for me. Big meeting. Thank you so much, Rebecca, to join us. Rebecca Ndlovu is a lawyer, not a public governance professional, and police expert with over a decade of experience in litigation, corporate advisory, regulatory compliance, and institutional governance. She holds a Master of Law in Energy and Environmental Law from the University of Birmingham, where research focus on the enforceability, Ghana nuclear liability compensation regulation. Rebecca has served her on several national board and governance bodies, including the legal board of the Mineral Income Investment Fund, the board of the Ghana Audit Service, medical board of the Ghana Audit Service. She currently an executive member of the Council of Foreign Relations Ghana and served on the board of Africa. A professional interest in energy, law, nuclear regulation, public policy, and government. She is passionate about supporting the development of effective legal and regulatory framework that promote the safe, secure, and peaceful use of nuclear technology in Ghana and across Africa, and across new common country for nuclear. Thank you so much. What is yours?
Thank you. Thank you so much, Lanssina. I really appreciate this opportunity. Now, the theme for today is the role of nuclear energy, role of the Nuclear Energy Agency in the shaping of international framework and future of nuclear. And I have the best people to speak to this topic here today as my guests, and I'm going to introduce them in a bit. Firstly, I want to introduce Madame Beatriz Hernandez Nalvez. She is the policy advisor and the global relations lead, OECD Nuclear Energy Agency. She serves as the policy advisor, as I said, and global relations lead, and she's responsible for advancing the agency's global engagement strategy, strengthening relations with government, international organizations, other key partners, and also providing strategic policy advice to support the NEA's international objectives. Madame Beatriz, before joining NEA, held senior positions in the Mexican Foreign Service in Paris, Geneva, where she specialized in multinational negotiations, international governance, strategic partnerships. She has extensive experience working with the United Nations organizations and other international bodies, leading high-level diplomatic initiatives and fostering consensus among a broad range of stakeholders. Ms. Hernandez holds a Master's of Science in Development Management from the London School of Economics and Political Science, and she has a bachelor's degree in international relations from the National Autonomous University of Mexico, a Mexican national. She speaks fluent English and French and Spanish. And today we are excited to have her here. So participants, welcome Madame Beatriz Hernandez. Now, thank you. Now,
Thank you very much.
Thank you too. Now, let me introduce Mr. Christophe Tocco. He is the head of division, policy and coordination, OECD Nuclear Energy Agency. And he assumed this role from 15th of September 2025. He provides vital leadership in supporting the NEA, Director General and Deputy Director General, and ensuring close integration and coordination of the many diverse activities underway in the agency. His responsibilities include overseeing strategic planning, international relations, programs prioritization, communication, publication, and serves as the Secretary of the Steering Committee on Nuclear Energy. Now, Mr. Tocco brings a wealth of expertise to the NEA based on his extensive international experience in policy making, and multinational coordination. Most recently, he served as the acting assistant administrator at the U.S. Agency for International Development's Washington Bureau of Policy, Planning, and Learning. He has also served as U.S. delegate to the Development Assistance Committee, DAC, at the OECD between 2018 and 2022. He's a French national who also holds a U.S. citizenship. Mr. Tocco holds a Master of Science in Innovation and Entrepreneurship from the Paris School of Advanced Business, where he advanced business studies, I beg your pardon, and he has a bachelor's degree in economics from the University of California, Los Angeles. He is originally from San Pedro, California. Participants, could you welcome our guests, Miss Beatriz and Mr. Christophe Tocco. Hi, distinguished guests. We are so excited to have you here. And we want to believe that in the next few minutes, we'll have quite a good time here. So are we ready to go? Maybe I should just get into it with the first question. Now, I want to direct the first question to Mr. Tocco. Can I proceed, Mr. Tocco?
Yes, please go ahead. We also have a presentation to provide as well, whenever you're ready.
Right. So just before you go into your presentation, can you take us briefly, just in a few minutes, what the role of the OECD nuclear agency, the role of the NEA is, and why its work has become increasingly important in today's rapidly changing global energy landscape. Just for 2 minutes before you get into your presentation.
So the whole presentation is going to cover answering that question.
That's okay then.
So I suggest we just start, because it will answer what the NEA does and what our role is within the international community with the global renaissance in nuclear energy. If you're okay, we could start the presentation.
Absolutely. I think we can dive into the presentation. You have the floor. Thank you.
Okay, thank you. Beatriz is going to start us off and present the slides. So welcome, everyone. Thank you for having us today. We're excited to share some news and happy to have questions from the audience when we're done with the presentation. I promise we'll be pretty quick so that you can ask questions.
Right. Thank you.
And Beatriz, go ahead. You're going to start.
Sure. Okay, here we are. Well, first of all, thank you very much again for the invitation to Christophe and myself to participate with this lecture. This is your first date. We will try to go as smoothly as possible, as is the end of the presentations for the first day of the summer school. Thank you, Florencia Renteria. She was contacting us for this presentation, and for all the team of the newcomers for Nuclear Global. Well, first of all, I would like to begin by talking about something bigger than just an international organization, a technology, or a policy framework. In fact, we are witnessing of what NEA Director General Magwood has called a new era for nuclear energy. Around the world, countries are rethinking basically their energy futures. Energy demand is growing rapidly, and nuclear energy is returning to the center of discussion about economic development, about energy security, and decarbonization. So the question really is no longer whether nuclear energy can have a role on all these aspects, but rather the question is how to build institutions, the expertise, and the international partnerships needed to make it happen safely and successfully. And within this bigger context is the agency of the Nuclear Energy Agency comes into place.
Right.
The NEA is the premier international platform for coordinating nuclear technology, policy, regulation, research, and education. What makes the agency unique is that, well, it doesn't build a reactor, the agency. It doesn't regulate facilities, or it doesn't neither operate power plants. But instead, the agency brings together the people who do that. Scientists, engineers, regulators, policymakers, academics, and the industry leaders work together within NEA to solve common challenges and share their experiences. NEA was founded in 1958, and since then has spent, well, from nearly 7 decades. It has helped countries to develop excellence in nuclear safety, in technology, in science, and environmental protection and law. I think that the main issue here, the main message that we would like to convey to you is that no country builds a successful nuclear program alone. Nuclear energy is, of course, a national endeavor, but success depends on international collaboration, and that's what NEA does. So the mission of the agency is mainly to assist its member countries in maintaining and further developing, through international cooperation, the scientific, technological, and legal basis required for a safe, environmental, sound, and economical use of nuclear energy. But our role goes far beyond the technical support. It also provides authoritative assessment on key issues related to nuclear energy policy. Right now, the agency brings together 34 countries from across Europe, North America, and the Asia Pacific. These countries altogether represent the world's most experienced nuclear programs and account for about 82% of the world's installed nuclear capacity. More importantly is that the agency provides the environment to bring a community of over 3,500 experts from countries all over the world that participate in different NEA activities. In fact, the agency works in different ways. First of all, through its committees and its working groups. As I said, it's about 3,500 experts participating with all the committees, working groups, expert groups, all the different bodies within the agency. But secondly, also the agency shares its experience through different events, conferences, workshops, seminars, and trainings that take place during the year. More or less, we are talking about 200 events during 1 year within the agency. And thirdly, the agency shares its experience through publications and flagship reports that provide governments with the credible evidence-based analysis for taking strategic directions and decision-making. So for you, to give you an idea, this is a general committee structure within the agency. We are talking about 7 standing committees, more or less 74 committees, working parties and expert groups, and 2 high-level groups that report directly to the main body, which is the Steering Committee for Nuclear Energy. But of course, the agency doesn't work only with governments. This big network, as I was speaking of, 3,500 experts, also include international organizations like IAEA or the International Energy Agency within OECD as well, but also the global nuclear industry, associations, research institutes, think tanks, and the academia. In fact, NEA works with a multiple number of universities and research centers that are part of this big community. And when speaking with a partnership with international organizations, usually many people often ask us the question or are a little bit confused on what is the difference between IEA and the NEA. Well, basically, the Nuclear Energy Agency is a part of the OECD and is based in Paris. It's it has a membership of 34 member countries, primarily, as I mentioned, the advanced nuclear economies, with extensive technical expertise and mature in nuclear infrastructure, while IEA is mainly a universal organization within the UN system. In terms of functional focus, IEA and NEA differ importantly in the sense that IEA concerns mainly to non-proliferation and safeguards, while NEA has no role in these two areas and focuses mainly on safe and efficient use of nuclear agency, but also on economic and policy analysis and on advanced research on different types of reactor, including SMRs, which are quite of importance during the last years. I think that will be it. I will come later on with some other slides, but I give the floor to Christophe.
Great, thank you so much, everyone. So that was a great explanation from Beatriz on who is the NEA, what is this organization, and who do we collaborate with and how we work. Now I'm going to get into a little bit more about what's going on internationally and what the global nuclear space looks like with some statistics and information. So one, I think this slide is really to recognize that just a few years ago, most countries were planning nuclear phase outs. Many countries in Europe were not looking to build new nuclear. They were looking to get out of nuclear. And particularly after the accidents in Fukushima in 2011 and Chernobyl in 1986, that drove some countries to do referendums. For example, in 1987, Italy had a referendum and they decided to move out of nuclear completely, even though they had been a trendsetter. But just 3 days ago, they are looking like they're set to approve a legal framework for advanced nuclear. So they're looking to get back into it. So I think that's one of this important things to consider, is that in the past few years, there have been a few important changes geopolitically that have made the world reconsider nuclear. And I'd say that the three main changes have been the war in Ukraine, which disrupted the Russian gas supplies to Europe, the war in Iran now, which is disrupting oil supplies, and then the push over the last 20 years to get to a net zero targets for our energy, knowing that nuclear contributes to net zero targets. So let's go to the next slide. So this slide is about commitments that countries are making. So at COP38, there were 25 countries that committed to triple nuclear energy by 2050. And that number has since increased from 25 to 38 countries that were signed on at the 2026 Nuclear Energy Summit in Paris. So new countries include Belgium, Brazil, China, Italy, and South Africa. So many countries in the world are recognizing that in order to reach net zero targets, they must include nuclear power within their energy mix. Let's go to the next slide. So this slide is a big picture slide that looks at how the world generates electricity today on the left side. And on that side, you'll notice that nuclear, along with wind, is the second largest low carbon source of electricity globally, and hydro is the first. On the right side, you're going to see how electricity generation has expanded since 2010. And although there's been a lot of talk about climate and net zero goals, both from 2010 to 2024, the world has increased its CO2 emissions. And that's mainly because there have been new global coal-fired plants built and gas plants that have been built. So that's an interesting fact to understand. And the next slide, yes, next slide, yeah. So again, looking back, I mentioned the war in Ukraine, which affected gas supplies, the Russian gas supplies in the Middle East. war, which is affecting oil supplies currently. And then this renewed global awareness has led to more countries thinking about energy security. But they have to think about energy security within this triangle of energy security, affordability, and sustainability. So for each country, they have a different set of parameters with regards to what's available in their country or in their region and is sustainable, what's affordable to them, and how important energy security is to them. So let's go on to the next slide. So I understand many of you are from emerging countries, and that is certainly an area where there's been a huge increase in interest and desire to implement new nuclear energy. Part of this gets at the statistics that if you look with the percentage of people who don't have access to electricity and where they're highest, you can see that on the global map there. And we also know that for economic development to happen in a country, you need access to electricity for small businesses and large businesses and to do transformation in agriculture and industrial sectors. So access to electricity is particularly important in the global south, where we need it for people to have electricity in their homes, but also to power economic development. So this explains recent rise in really a strong interest in nuclear power across the developing world. And just to let you know, as a plug, in March, we co-hosted a conference with Kenya on nuclear energy and looked really at that very question. And next slide, please. Okay. So this slide is about SMR. So I'm sure you've read small modular reactors are very popular in the press and everyone thinks that they're the answer to many questions. However, one thing that is clear when you're working in the nuclear space is that there is no Ford Model T of SMRs quite yet. So the NEA has been tracking all the designs and this SMR dashboard, and you can see that there's over 127 different designs and technologies. Clearly, in the end, if you want to have a Ford Model T for small modular reactors so that you can get to the economies of scale required to actually make them cost effective, you can't have 127 different technologies. And so there's a lot of hope in SMRs, but it's still, I think what I want to emphasize here is that it's still hope and that there's still a lot of work ahead before SMRs become a actual thing that you can go and buy and use. Okay, next slide, please. So we have seen some progress since this return, the global renaissance. On the slide, you can see a few of the different areas of progress in the Western world. However, there are two big trends, I think, that we need to consider. One is that the long-term operation of existing fleets of nuclear power plants remains critical. Many plants in the US have had their long-term operation extended by 20 years to operate beyond 2040. There are many other plants that are looking at how they can extend the lifetime of their utility because it's the most cost-effective way to generate electricity. And then the second real progress we've seen is that the center of gravity for nuclear construction continues to shift outside of the OECD Western developed economies. So China leads the world in reactor construction. It's got 37 units under construction in addition to its existing 60. India has not the same numbers, but also has quite an ambitious program for expanding. While many OECD countries have announced ambition expansion plans, there's still a time frame to move from announcements to actually change. Next slide, please. So this slide comes from a new publication, one of the flagship publications of the NEA that was just launched last month, called the Nuclear Energy Outlook, which was looking at the goal of tripling nuclear energy by 2050, and then seeing whether we're on track to achieve it. And what it shows is that clearly we're not on track. The yellow part in the slide is the gap. And so, although this is all part of the IPCC and looking at how we can reach the goal of a 1.5% Celsius increase only in the temperature of the planet, we realize that if you actually look at the reality of what's being planned, and you look at the reality of SMRs and where they are in their development, that we have a huge gap between what people have committed to and what's actually possible at the current pace, unless governments really start to react. Next slide, please. So maybe this is a new acronym. FOAC is first of a kind reactors, and then small modular reactors we talked about, and policy issues. So on this next slide, we're going to talk about some of the challenges that come with each of those. So first of all, first of a kind reactors have been the typical way that we've been building large reactors in the West. They've had huge cost overruns and are very expensive because each plant that we build is a unique plant. In addition, in the West, we have supply chain problems because we haven't been building plants for many years, apart from probably South Korea. And so our supply chains have atrophied. In addition to that, we also have a need for new fuel cycle supply chains because Russia has become a major source of fuel supply for the West. And clearly with the war in Ukraine, that has become an issue that is of concern to all countries. So that's the first set of barriers. For SMRs, I sort of touched on the barriers that we have already with SMRs, which is that there's still a lot in planning, but there's not a lot that's actually, there's not a factory there that's ready to build hundreds of them one after the other, which is the goal eventually. But also, in addition to be able to do that, there have to be regulations all have to be modernized because SMRs bring different types of problems and regulatory issues than the large models that have come up till now. And so there's still many constraints to SMRs reaching their full potential. And then finally, the issue and challenge that lays ahead with regards to electricity markets. So current electricity markets are organized in a way that they often compensate generators based on short-run marginal costs, rather than the full value or the full system cost of electricity, which makes it so that nuclear is less cost effective. If you're only looking at 5 years ahead, what's the short run best way to reach your price point? Nuclear needs much longer time frames in order to become cost effective. Next slide, please. Okay, so this slide looks at industry. And basically, it was a questionnaire that asked industry what are the main constraints to expanding nuclear power. And they came up with the box comes up with 4 key constraints, and they're workforce, licensing and regulation, financing, and supply chains. And so what that really shows is that the problem really is not technological, but it's all these other elements that are constraining us. And particularly with regards to workforce, there's a rapidly aging workforce. And I think that's why this webinar is so important to be in this summer school, because we need to get young people interested in nuclear field and nuclear careers for this very reason, because there are going to be workforce shortages. Okay, next slide. So the NEA hosts an annual event that's called the NEA Roadmaps to New Nuclear Conference. It's our ministerial or our highest level conference. And we're going to be hosting the 4th edition in September next month here in Paris, and it's co-hosted each year with a different country. This year it'll be co-hosted with the United States. And it really looks at the challenges to financing workforce development for new nuclear. And what's particularly interesting about the conference as well is that it brings together government policymakers, but also the industry and companies that are looking to build new nuclear, so that there's a conversation between both sides on all the different bottlenecks that are that they're facing. And so with that, I'm going to pass it over to Beatriz again for the last few slides. We just have 4 more slides, and then we'll take all your questions. These slides that are coming next are about building the capacity building for the workforce. Go ahead, Beatriz.
Thank you very much, Christophe. Precisely, you mentioned that one of the main bottlenecks is not technology, but is rather the workforce in nuclear. And you mentioned as well that across many countries, a significant part of the nuclear workforce is now approaching retirement. And the demand of new talent is increasing. So at this current moment, the competition for engineers and scientists is very intense, whether it's in the nuclear sector, in the artificial intelligence, digital industries, space technologies, or advanced manufacturing. The real challenge here is whether enough young people as you are choosing nuclear careers in the first place. So really the future of the sector depends very much on the next generation of experts and professionals. And that's why the agency has given particular emphasis to this area of work. So in these slides, we resume what are the main challenges in terms of attractiveness, the workforce gaps, and the training and education to build, again, the new generation of experts. And we are going to present to you some examples of the initiatives that have been developed by the agency to build precisely this generation. I will first start with the new NIA Global Forum on Nuclear Education, Science, Technology, and Policy. It was created precisely with the intention to connect academia, policymakers, and industry. It's the first international standing platform dedicated to bring all of them together. And for newcomer countries, this is particularly valuable. As we have mentioned in numerous occasions during the lecture, not every country can build every capability alone. So international cooperation is really of the most importance. The Global Forum helps universities to share the best practices, also to align educational efforts and participate in discussions on the future of nuclear technology and policy. And most importantly, it gives students and educators a voice in shaping the future of the sector. One of the particular initiatives that I personally am very excited about is the Rising Start workshops. Normally, for these workshops, 40 international students are invited. Mainly female students and researchers, with the idea to present the research, to receive mentoring, to develop leadership skills, and most importantly, to become part of an international community that will shape the future of nuclear energy. In reality, the underlying message of this workshop is very powerful in the sense that talent exists everywhere, that opportunity not necessarily always reach the most talented, and that's why the purpose of the program is to help close this gap. I will also like to mention to you the nuclear education skills and technology that we usually call the NEST framework. This is an interesting opportunity. It's a joint project, a flagship program for developing the new generation of nuclear experts. The NEST framework is part of it participates 15 participant countries are part of NEST with 6 projects, and so far more than 200 fellows have participated in the program. It provides fellowships, multinational research projects, and hands-on training and access to world-class facilities. Students and young professionals work directly with experts, laboratories, regulators, research centers, and industry partners. And what makes NEST very unique is that it focuses on learning by doing. So it really tackles the projects that are dealt with, tackle the real issues or thematic areas that are important for the industry and for the academia. It's important to note that only the universities of participating countries can be part of the framework, but this is not limited to NEA members. So it is open to other countries, to other institutions, but only they need to comply with the requirements to be part of the framework. I think well, and part of the challenge in the workforce development in nuclear sector is precisely how to fill the gap on the gender balance. And for that, the NEA has been very much in advance in thinking on how to report, because what we don't see, we cannot improve. So there was this flagship report launched in 2023 that takes stock of current gender balance in the nuclear sector in NEA countries. This document was the first public international data on the subject, and it allowed to establish a policy framework with particular recommendations on how to, again, reduce the gap in the nuclear section for women, with a vision to attract, but also to retain and advance the position of women in the sector. Just right now, a new survey was launched in this year, and we expect that the information provided by the survey will allow us to have a more updated information to follow up on the previous report of 2023. So with this information, I think we have finished the slides, and we will very much welcome any question or comment that you will have for us. Thank you very much.
Thank you so much for that erudite presentation. I believe that, in fact, before we started, if you had a few questions regarding the NEA, you would realize that most of them were answered in the presentation. We saw quite a number of new things that we learned. So I would, whilst the rest of the participants, whilst you prepare your question, if you have a question, let me know. But I have a quick question to ask, if it's okay. And I want to ask Mr. Tocco, if that's fine. Now, many African countries, are seeking to explore nuclear power now. And what do you think are the major policy mistakes that you observe among these newcomer countries, and how do you think you can avoid them?
Okay, thank you. I also wanted to note that in the chat, there's a few questions that we can also maybe answer as well.
Right, okay.
So I don't think it's not about major policy mistakes. It's more that for a lot of African countries, they're embarking on the journey. And so it's the whole establishment of a regulatory and legal framework takes a lot of effort, intergovernmental coordination, and legislation, basically. And so what that really requires in many contexts is a lot of support from the top. So where the president or the leader of the country is very clear that they want nuclear power to be part of the energy mix, because it takes years to put in place that kind of a framework and the legislation required. And so you see Kenya has been really clear about that. I mean, obviously South Africa already has nuclear power, but you see Kenya is really serious, and the president's very serious about that. You see Rwanda as well being extremely serious about looking into putting in place all of the different stepping stones that are required. So that would be my answer to that.
Okay. All right, that's fine. Thank you very much. For our participants, if you have a question, kindly you state your name and the country you came from, and then we are going to read your questions. So I'm going to take one. Okay, I'm going to take one question from, there's quite a number here. Let's take one from Bromod Badia. And you didn't state your country, but that's fine. Your question is, what is the process of a newcomer country organization to be a member of NEA? So if Beatriz, you could take that question for us.
Sure. Well, let's say that this is a step-by-step process. As we mentioned, there are a number of opportunities for non-members to engage with the agency, either in even different events, conference, workshops, under different joint undertakings, joint projects that the agency has, which, as I mentioned, are part of are available to non-member countries. So I will say that the first step is to engage with the agency in the different ways. Secondly, we have, as part of our global relations strategic directions, which are also come from the OECD framework, a different status of participants, either as invitees, as participants, or as member countries. As invitees, basically a country can express interest in participating in a standing committee or its subsidiary bodies, expert groups, working groups. And a decision is taken on this particular working group or expert group to invite this country to participate as observer during the discussions of this particular committee. So that will be a second stage. So as participation evolves, a country can become a participant to a committee, which gives more influence in the work and in the way they engage with this standing committee. And based on that, and as it evolves, the engagement with the agency, a country can request formally to become a member of the organization. The main principle for becoming a member is the mutual benefit from the country and to the agency. So this is the main driver that the steering committee looks at when evaluating, when analyzing the proposal of a country to become member of the country. So that's why I was saying that it's a step-by-step process in engaging with the agency. And of course, when there is a formal request to become a member, there are a number of steps that have to be followed. But I will say that for a newcomer country, the first thing to do is start engaging with the organization in the different options and processes that they can participate.
Right. Okay. Thank you so much. I think Clarice Falanga had a similar question. I think that was the same question from, yeah, okay. That's the same question from Abdul Rahman from Malaysia. He also asked questions about how a newcomer country could join NEA. So I think all of you have your questions answers. Now, let me quickly ask this before we proceed. You know that for every for a newcomer country or any country that is seeking to go into nuclear energy, a strong regulation is often described as a foundation of a successful nuclear program. What would you say are the characteristics, that distinguish an effective nuclear regulatory framework? Beatriz, do you want to take that, or Mr. Tocco will take that for us?
Yes, sure. Thank you.
Okay,
I think
thank you.
one of probably we have a document called the Green Booklet on Trusted Regulators, which is a compendium of what experts have said are important elements to be a good regulator. So I commend people to, all of our publications are available online, or I can get them the links to them to the organizers afterwards. But the one most important thing when it comes to nuclear regulators is independence. They have to be independent and be able to make their own decisions, because otherwise they're unduly influenced, and then the safety aspects will come into question because they don't have the independence to consider those. So to me, that would be the most important aspect.
Right.
Regulators also have to have a strong engagement with citizenry and communities around where the nuclear plants are, because there has to be an acceptance by the local populations. And so this ability to communicate with the population is very important. They can't just be sitting all alone and saying, here are the regulations, because nuclear power plants happen in a community and people are concerned. And if people aren't happy about it, they will let you know. And in many cases, a big issue is the communication with local communities.
Right. Okay. Thank you. We're going to take a question from Johnson from South Africa. And Johnson has two questions. So Beatriz will answer one, and then Mr. Tocco answers the other one. Now, the first one will go to Ms. Beatriz, and it says that with the recent push for net zero targets by 2050, how is the NEA currently shifting its policy support to help member countries accelerate the deployment of SMRs? Let me take it again. He says that, and his question is on the global policy shifts. Okay. He says that with the recent push for net zero target by 2050, how is the NEA currently shifting its policy support to help member countries accelerate the deployment of SMRs? So whilst you're preparing for that question, Ms. Beatriz, let me read the second question so that Mr. Tocco can also prepare. The second question, which Mr. Tocco will handle, is on international collaboration. And the question is, what is the biggest challenge that agencies face when trying to harmonize safety regulations across member countries with deeply differing nuclear legal frameworks? Let me take it again. What is the biggest challenge the agency faces when trying to harmonize safety regulations across member countries with deeply differing nuclear legal frameworks? Right. Thank you. So if you're ready for us, Ms. Beatriz, we are. Yes, if you can answer the first question. Thank you.
Well, thank you for the question. In fact, the agency has been working on SMRs from some time now, and it's already changing the policy dynamics concerning this new technology. In fact, there are quite a number of working groups and expert groups that deal with the different aspects of SMR. When Christophe gave his presentation, actually, he mentioned also the SMR dashboard, which provides a framework in which there is an analysis of all the different technologies related with SMRs. And this has to do basically with what I mentioned at the beginning, one of the ways the agency influence policy, which is because of this analysis that are made through publications. So first of all, we provide publications with analysis on these new technologies. Second of all is we have these old working groups and expert groups that deal with the different aspects of SMRs. Christophe also mentioned that, well, we deal with regulatory aspects for SMRs, with waste management, nuclear waste management concerning SMRs, their regulatory framework. So all the different aspects related with SMRs are already topics that are central to the program of work of the organization. But as I said, we are a community of experts, and those experts are the ones coming to the different bodies and providing their expertise and in a consensus building manner, deciding on what should be the best way to proceed concerning these technologies. So this is a work made within all these networks and that influence the policy that of the agency and of the agency through the different countries.
Right. Thank you so much, Ms. Beatriz. Now we go to Mr. Tocco for answer to the second question.
Sure, thank you. So first I wanted to thank Johnson for that question. It's a really interesting one. And it's interesting the way he posed it. What's the biggest challenge for the agency? So being the agency, we see all the different countries and what they're doing. And we see that harmonizing regulations is an important factor to deployment, right? So basically what happens now is, as Johnson seems to understand, is that each country has its own national sovereign framework. And if you want to implement the same nuclear power plant that was already built in the US, you still have to do all the steps of the regulatory environment in that new country. And that country's sovereign entity has to make a determination. So what that means is the deployment of any type of technology can take years and years across multiple different countries because every single regulatory agency is reviewing them independently, as is their sovereign right as a nation state. So the agency sees this across the board. But so what we can do is we highlight to the countries that this is a big impediment to deployment. Now, if you recall, every time there's a nuclear disaster, so let's take Fukushima, safety becomes the biggest and most predominant issue. And so no one will spare any moment or any time for safety, and it could make things delay for years and years, but we'll make sure that there's 100% safety. We're reaching a time where that pendulum is swinging a little bit, where people are looking at the need to deploy nuclear energy, and you see the US has been adjusting its regulations and trying to make it so that it's easier to implement. And so the question is, how do you build the right balance between an ability to deploy in a way that is safe? And so it's clear that if we want to deploy and reach these goals of tripling nuclear energy by 2050, or even reaching the goals of the Paris Agreement on climate change, that we need to figure out how to harmonize some way the regulations. And there is no clear answer to that question at this point, other than that the NEA can bring together all the countries and make them identify that this is a deployment challenge and ask them how they would like to work together on the issue. Hopefully that's answers partly the question.
I think so. Thank you so much. Now, Ezekiel, Ashai, you have your hands up. You want to quickly ask a question? Ezekiel? Okay. You have the floor. Can you ask your question? Right.
Yes, thank you very much, Madam Rebecca. My name is Ezekiel from Accra, Ghana, representing Wem'Afrika. I think my question is answered. It's just like the Johnson. So we have Ghana that is also coming up with our nuclear technology program. And like Johnson said, we have different countries with geopolitical interests and regulatory capacities. So the question is, how does the NEA make sure that we have an effective international nuclear framework? I think it's the same thing like what Johnson asked, and it's been answered. Thank you very much.
Okay. Thank you, Ezekiel. We're grateful. Now, I want to quickly dive into access to capital financing, and if Ms. Beatriz would do me the honors, what would you say as, the innovative risk sharing models or policy instruments that are required to finance the tripling of the global nuclear capacity by 2050? What innovations, what policy instruments do we have to put in place to finance the tripling of the global nuclear capacity by 2050? Yeah. Ms. Beatriz, you want to take that? Thank you.
Not an easy question.
I know.
As you are aware, there was a policy shift, a relevant policy shift by World Bank in 2025, in the sense of opening the door to finance nuclear programs, which were banned for many years. So this openness has also spread through regional development banks. And what the agency has been doing since 2025 is precisely engaging with the World Bank and with the other regional development banks to make them aware of the different safeguards and regulatory framework that exists already, that are in place, in order for them to give them confidence on the need to finance these development nuclear programs. So it's a question of engaging with the multilateral banks to explain the different frameworks in place, to also advise countries on how to precisely make the necessary changes for the nuclear programs in order for them to be confident enough for investors to give their necessary resources to implement them. So this is mainly what has been done by the agency, and actually this is a key topic, a pillar of the discussions that are taking place in the roadmaps conference that take place every year in Paris. Christophe mentioned the conference that is taking place this year in September, and which is co-chaired by the US together with NEA.
Okay, thank you so much. I think our time is up, so our speakers will have just a minute for their closing remarks. And, in closing, I want to ask, if we are to meet here in 2040, what would you hope the global nuclear landscape will look like? Just in closing, firstly to Mr. Tocco and then Ms. Beatriz also, just a minute, and then we can just wrap up here.
Sure. So if we meet again in 2040, I would hope that nuclear power is accessible to more countries than it currently is, but also in a way that is safe and secure, because we know that it's imperative for meeting climate and environment goals. So that would be one thing. There was also just one question in the chat that I wanted to briefly answer, which was about security and safety challenges associated with SMRs. And I think that's a very smart question. I don't think enough thought has been put into that, because right now we don't actually have an SMR model to, sell to country X or Y. But the question, how it intertwines with terrorism and the necessity for securing the sites, even of SMRs, and what that's going to cost and how that increases the costs, and then how do you deal with the waste? So there's a lot of questions exactly that the NEA is helping to think through as we get closer to the deployment of SMRs. But anyway, I wanted to thank everyone for their interest, and I hope it got you interested in careers in the nuclear sector. And if that's the only thing that it did, then we achieved success. Thank you so much.
Yeah. Thank you so much. Right, Madam Beatriz, your closing remarks?
Christophe mainly said almost everything, but if I should resume that, I will expect to have a safe, efficient, and diversified nuclear sector that is fit for purpose for economic development for all.
Right. Thank you so much. I want to say special thank you to our guests, Madam Beatriz Hernandez Narvaez, and also Mr. Christophe Tocco, all from the OECD Nuclear Energy Agency. I want to say a big thank you to you for your time. This has been very informative, very interactive, and we have learned so much from it. I want to say special thank you to all participants, all organizers. Thank you for your time. We want to hope that you will put to use all that has been learned over here in order to have a very good nuclear future that we are all looking up to, right? So thank you all so much for your time. I think there's the last section for today. We want to hope that you joined the next session tomorrow. Thank you all. Have a good day. Bye-bye.
Thank you.
Thank you very much, Beatriz and
Thank you,
Christophe,
bye.
for the wonderful support. Just a few announcements before we close for today's session. And we say goodbye to our distinguished speakers, and we want to acknowledge the great support of the Nuclear Energy Agency. On Wednesday, we also have one of the experts in the house, Alexia Mercier, who will be also addressing some of the questions about radioactive waste management, that she kindly connected us with Beatriz and Christophe to make this lecture possible. So we remain in deeply cooperation with the NEA, and we really appreciate all the great efforts and all the great initiatives that are being spread around the community. So thank you very much, Beatriz and Christophe, for your participation. We are deeply grateful for it.
No, thank you, Florencia. And maybe a last word, if I may, just if you are interested in knowing more about the agency, we really encourage you to go to the web page and to follow the agency through social media. A lot of information is available publicly. So really, if you are interested in the different technical aspects of nuclear, you can have access to all these documents and engage with the agency as much as possible. Thank you very much.
Thank you so much for that, Beatriz. And of course, we will share also the official website of the NEA and any other resources. And also, if there is any other potential projects or additional cooperation from our participants, we will direct them to both of you. So we are very grateful for it.
Thank you very much.
Thank you so much. And dear participants, we hope that you are not very tired from today's first day, but we have prepared very 10 days intensive program. And before we close, for tomorrow, we kindly ask you if you can log in 10 minutes before we start, that you can check your camera, your audio, the microphones and everything. We kindly ask you, of course, also to stay muted, that the speakers can do their lecture smoothly, because sometimes we can have some noise in the background, that it is avoiding others to listen to the lecture. The recording for today's day will be also available in the YouTube channel. So tomorrow we have 3 lectures to cover. One is starting with Nuclear Safety Culture by Ken Clopes. He's a former member of the House from the United States. And also we have the Polish perspective from Mrs. Ewelina Pomianowska. She will be speaking about electrical systems and fire safety in nuclear facilities. And last one, but not the last, and not the least, Mr. Dirasante Banantan from Ontario Power Generation. He will be addressing the perspective from nuclear plant operations and emergency response. So we really hope that you have enjoyed the first day, and we look forward to seeing you tomorrow. Please, Lanssina, over to you. If you have some last words for the participants, we will appreciate that.
Your participants are very, very tired. I have only one word for them. Thank you so much to join us and to contribute to make summer school very big. Thank you so much.
Thank you so much, Lanssina. And please, if you haven't been part of the WhatsApp group yet, we are encouraging you to join us, to interact in the chat, or to address any immediate questions or requests that you may have. And we thank you deeply for today's session. So we hope that you have a very good rest of your day, depending where you are. And we see you tomorrow. Please take care, and all the best from the team and the partnership organizers. We really thank you for today's session.